బాబాయ్
చెప్పా
ఎక్కడున్నారు బాబాయ్?
కాలేజీలో
తెలీదా కాలేజ్కి?
వచ్చిందా?
ఓకే. ఇది వేరే వాళ్ళ లాగిన్ లో చేస్తే అవుతుంది, మన తొందర వేసేస్తే అయిపోతుందని అట్లా.
అదే మరి నీకు ఇచ్చిన కదా రవి డాక్యుమెంట్స్ అన్ని.
చెక్ కూడా కావాలి కదా మనకు, అది కంప్లీట్ చేయాలంటే చెక్ కావాలి.
మరి ఎప్పుడు వస్తావురా సాయంత్రంతో?
మీరు ఒకసారి కాల్ చేయగలరు. ఈవినింగ్ నాకు గుర్తులేదు, ఈవినింగ్ నాకు తెలియట్లేదు సరిపోతుంది.
సరే నేను చేస్తుంది.
ఒకటి 37,000 లాగిన్ కొట్టినా అది వేరే బదిలాడు ఆమె లాగిన్ చేస్తాయి.
అవునా? సరే నేను సాయంత్రం.
సరే.
వస్తున్నాను. Good morning, sirs.
Good morning.
Good morning, sir.
Good morning. Good morning. Good morning, everyone. Is there on the
Morning,
line?
sir.
Good morning, 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 sir.
Morning.
గుడ్ మార్నింగ్ సాంబశివరావు గారు.
Sir, good morning. అదే
వినిపించట్లేదు సార్.
వాయిస్ రావట్లేదు సార్.
సార్ వాయిస్ ఎవరిది వినపట్టలేదు సార్.
ఇప్పుడు ఏం పడుతుందా?
ఇప్పుడు ఓకే సార్.
Yes, sir.
ఓకే సార్ ఓకే సార్.
హలో
ఓకే
Sir,
సార్.
good morning, sir.
సార్ గుడ్ మార్నింగ్ సార్. నేను మాట్లాడింది వినపడుతుంది పిల్లగాళ్ళతో. సార్ చూడండి, మీరు మాట్లాడండి, బయట కూర్చుంటాం.
Yeah, you're audible. Srinivas, you're audible.
సార్ నమస్తే సార్. ఓకే సార్, వినిపిస్తుంది.
సార్ ఇప్పుడు నాది ఎక్కడ కనిపిస్తుంది సార్? సార్ ఇలా రండి, ఇమేజ్ కనిపించింది. ఇది బంద్ చేయండి.
ఇప్పుడు ఇది మ్యూట్ లో ఉన్నట్టు కదా, ఇది మ్యూట్ లో ఉన్నట్టు కదా.
స్పీకర్స్ హలో
హలో,
కొంచెం దూరం ఉండమంటారా? అయితే నేను నా సిస్టమ్ మీద ప్రాబ్లం.
హలో సార్, సాంబశివరావు గారు వినపడుతుందా? సార్ సాంబశివరావు గారు వినపడుతుందా? చూస్తాను.
అదే
మనం చెక్ చేసుకుంటే
అందులో కనపడుతున్నాం చూడండి. అంటే మనకు కనపడతలేదు.
ఓకే సార్.
యా హలో ప్రిన్సిపల్ సార్, గుడ్ మార్నింగ్ సార్.
Good morning, Samsarao garu. Good morning.
రాజ్ కుమార్ సార్, గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ సార్. రైట్
సార్ ప్రిన్సిపల్ సార్, గుడ్ మార్నింగ్ సార్. రత్న ప్రసాద్ సార్.
Good morning, sir. Very good morning, sir.
మేడం అది ఎందుకనో ఆయన మన దగ్గర డిస్టర్బెన్స్ వస్తుంది, దూరంగా ఉండండి, అన్ని అన్మ్యూట్ చేయండి, ఇద్దరు తప్ప అంటున్నారు. అది అన్మ్యూట్ చేసిన దాని నుంచి రాదు. అక్కడ సార్ దగ్గర చెప్పండి. స్పీకర్ కూడా బంద్ చేయాలి సార్.
Hola, good morning, everyone.
Good
I'm
morning,
Anjali.
ma'am.
Good morning,
madam.
Very good morning, madam.
Good morning,
Bonara,
ma'am.
Good morning, ma'am. Good morning, ma'am.
Okay. Okay. I'm Anjani, IQSC coordinator of this SRN BGNA Government Arts and Science Autonomous College, Khammam. Good morning, all the dignitaries and the delegates who have gathered here on this occasion. An amiable welcome to all on the occasion of one-day national webinar on concepts of real analysis by the Department of Mathematics of our college.
Okay.
First of all, sir, I'm very glad to invite our head of the Department of Mathematics, V. Sambashivarao sir, the webinar convener, to give a welcome address on this platform. Welcome, sir.
Thank you, madam. Good morning, everyone. The Department of Mathematics, SRN Regional Government Arts and Science College, Khammam, welcomes you to this webinar with a warm heart. I thank you all for registering to the webinar and being part of this program. First of all, I would like to thank our beloved Principal KSS Ratnaprasad sir for his support and encouragement to conduct this webinar. And he always stood like the backbone of the college and always support and encourage us in every aspect. And also in recent times, under his guidance, nearly 6 seminars were conducted. This is the seventh one we are going to conduct here. Now, I must thank our eminent speakers, Dr. L.P. Rajkumar sir, head of the Department of Mathematics, Kakata University. And also, I would like to thank our another speaker, Dr. R. Baravi Sharma sir, Assistant Professor, Department of Mathematics, Kakata University. Hello, sorry for interruption. When we approached Rajkumar sir and Baravi Sharma sir and put our proposal before them to conduct a webinar on real analysis, without any delay, they agreed our proposal. They accepted to be the resource persons of this seminar. It shows their interest to do something to the benefit of teaching fraternity. And also, I would like to thank Srimati Anjani Saraswati, IPSC coordinator of this college, for accepted to be the moderator of this program. Actually, in recent times, we have conducted more than nearly 6 webinars. Almost all webinars, she has been the moderator of all programs. So her patience is very much highly appreciable at this here. And also, I would like to thank my colleagues of the department for extending their support and encouraging to do this webinar. I affirm that this webinar is the result of our teamwork, not the credit of a single person. And also, I would like to thank all the faculty of all the family members of SR Binjar Government Degree College, Khammam, for their support and encouragement to conduct this program. Finally, I would like to share the intention behind the selection of the topic, the concepts of real analysis. So, all of you know, many of the faculty and students also feel very tough, either in teaching and in understanding real analysis. So out of all the 6 papers at UG level, we must agree that real analysis is the toughest paper. So not only for the students, but also for the teachers. Teachers also facing many problems to making the students understand the concept in real analysis. So at this scenario, we have decided to conduct a webinar on real analysis, and we have selected this topic so that everyone can get something and everyone will be benefited, and it would be helpful to everyone to enhance their teaching efficiency. So at the end of each session, you can ask your questions and get your doubts clarified. You can ask directly, or you can keep your questions in the chat box also. So I hope all the participants will make use of this webinar in a proper way and Let us all make this successful and fruitful. Thank you. Thank you very much.
Okay, thank you, sir. Thank you for sharing your outcome of this webinar. So, and thank you for, personally, I thank you for appreciating my patience. Now, I consider it my honor to welcome our dynamic, kind-hearted, young-minded principal sir and chairperson of this webinar, Sri K.S. Ratna Prasad garu. Welcome, sir, to give his valuable remarks on this occasion. Welcome, sir.
Thank you, ma'am. Thank you for your kind words always. Good morning, everyone. On behalf of the college, staff, and students, I once again welcome you all for this webinar. This sort of webinars will definitely enhance our knowledge and also help us to hone our skills. Mathematics is a very difficult subject right from the word go. I appreciate the Department of Mathematics of our college for organizing this sort of webinar. Already our college, as rightly our head of the Department of Mathematics, Samaswara Garu, pointed out, we have been organizing webinars since the pandemic. These the backbone behind this sort of webinars is none other than our Honorable Commissioner of College Education. He enthused us, all the teaching fraternity in all government degree colleges to take up this. As all we know, once again, mathematics is a very tough subject. Our head of the department also said that real analysis is very difficult to comprehend and also difficult to teach. I hope every participant will take a leaf out of the experience of Dr. Rajkumar sir and Dr. Sharma sir with their lectures. Thank you, Dr. Rajkumar sir, and a big thank you for Sharma sir for accepting our invitation and delivering lectures. Thank you once again, all the participants. Happy learning. Thank you, Amma. Please take over.
Okay. Thank you, sir. Thank you for your supporting words and thank you for your precious presence with us. And now it's time for inviting our esteemed resource persons. It's my honor to invite Dr. L.P. Rajkumar, Head of the Department of Mathematics, Kakatiya University, Warangal, on the topic continuity and uniform continuity of functions. Now I request Srimati K. Jyotirmayi Rani to introduce our resource person.
Good morning, everyone. Thank you for being with us this morning. I feel pleasure to extend my warm welcome to all for the webinar on the concepts of real analysis. I feel privileged to take an opportunity to introduce our today's resource person, Dr. L.P. Rajkumar Garu, on behalf of our college. Dr. L.P. Rajkumar is the head of the Department of Mathematics, Kakatiya University, Warangal, since 2019. He was awarded PhD under the guidance of Professor Malla Reddy from Kakatiya University in the year 2011 with title Study of Internet Router Using Matrix Queuing Theory. His research area include internet traffic modeling, stochastic process. He joined in Kakatiya University as assistant professor in the year 2007. He presented his research paper at International Conference on Communication Systems and Technology, San Francisco, USA in the year 2010, where his research paper was selected for Best Paper Award. He was the chairman for a national level technical symposium in the year 2012. He was elected as Associate Fellow for Telangana Academy of Sciences in the year 2015. He was the organizing secretary for an international conference on vibrational problems. He has completed a major research project funded by University Grants Commission in the year 2017. He has published 15 research papers in both national and international reputed journals. Moreover, authored and edited 6 textbooks for BSc Statistics and Mathematics students. He served Kakatiya University with various responsibilities. He was the principal for the University Engineering College from 2011 to 13, and University Nodal Officer from 2013 to 17, and Additional Controller of Exams from the year 2017 to 19. He was the Chairman, Board of Studies in Mathematics from 2017 to 19. And at present, 3 students are pursuing their PhDs under Sir's guidance. This is the brief introduction of Dr. L.P. Rajkumar Garu. Sir, we feel honored to have you with us. You have made all of us proud of your distinguished work in numerous capacities. I also thank you, sir, for providing your gracious presence to join us and enhance our knowledge. Now, I welcome Dr. L.P. Rajkumar Garu to share his expert opinion on continuity and uniform continuity of functions with all the participants gathered here. Over to you, sir. Thank you.
Thank you, madam. Thank you very much. I thank Dr. KSS Ratnam Prasad, who is the patron and principal for SNR BGNR College. And I thank the moderator, Srimati Anjani, who is a IQAC coordinator. And I came to know that you are organizing a number of programs. And I thank the convener of this program, Sri Sambashiva Rao, who is also the board, one of the member of the Board of Studies in Mathematics, Kakti University, and the coordinator K. Srinivas, and all other organizing committee members. And I also thank Jyotirmaya Rani for introducing me to the audience. And thank you. And it's my privilege to be a part of your conference. I am really thankful to the organizers. And the title of my talk will be on continuity and uniform continuity of functions. We have already organized one program on real analysis. It was a faculty development program on real analysis, where we had a 6-day program. I had an opportunity to take the continuity of functions on that FDP. And when Sambashiva Rao sir and others asked for me to take a class, I accepted that because I had already given a talk on continuity of functions. It is only that to an additional part, I've added uniform continuity. The talk will be same, and those who are present in that FDP will be having the same, but in elaborative way, that's all. And the contents on my talk will be of this form, and I'll be having in this continuity. And I'll be introducing what I mean by continuity and what is the motivation for the continuous functions and where we study and why we study the continuous functions and real-time applications of continuous functions and who were the contributors, who were the mathematicians who contributed towards this continuity of functions. And I'll be giving some definitions and some examples on the limits. And then I give the definition and examples on continuity of functions. And I give inverse functions and continuity and some theorems and examples on continuity of functions and where in general it is used as research publications, as in research publications. And I give some definitions and examples for uniform continuity of functions and some theorems. And then some how the teacher has to be in the present age situations. In coming to introduction, continuous is just a mathematical term. And if you are defining a color, and the color may be blue, red, and green, depending on the property of the color what we are using, we define that it is blue, red, or green, and so on. So unlike the same terms, we define continuous as a mathematical term. It's not a tool or a process or an algorithm or a theorem. It's just a word that refers to a special type of function. So continuity or continuous is a special type of function. This is same as that we use it for any other function. So continuity is not any term that is to be confused. The theorems and algorithms can be applied, but definitions and the terminologies that cannot be. Theorems and algorithms, whatever we discuss in this continuity. They can be applied only, but the definition of continuity or the properties, they cannot be changed. And motivation to this continuity is it provides a natural how we define 3 to the power of root 2 or 7 to the power of pi. When we have first introduced exponential, we thought about a to the power of b, and suppose that we are given a to the power of b, it means that a is multiplied b times, where b is an integer. When b is a rational number, like 5 to the power of 1 by 2, it's also not to do hard very to think that it is a positive number, and it gets 5 by multiplying itself. We get a real number 5 when it is multiplied by itself, and it's nothing but root 5. However, it's very difficult to explain 7 to the power of pi means naturally that it's a number, that's a sequence 7 to the power of 3, 7 to the power of 3.12, and so on. Eventually, it goes closer to. The continuous preserves the limit of sequence. Any real number is a limit of a sequence of rational numbers. Therefore, if a real number, a real continuous function, and we know its value on a rational number, we know f. In other words, the continuous function is a function which is mapping R to R and can be uniquely determined by its value on Q. So continuous functions are preserve the limit of sequence, and what I mean by limit of a sequence is it can be approximated to the sequence of functions. And motivation to this is, and I would like to urge two main reasons to study continuity. The continuity functions have a beautiful properties like intermediate value theorem, and it's a property for connectedness. Having some disturbance. The continuity functions have beautiful properties like intermediate value theorem, and it is for connected domains, and the limit can be put inside the function. The compositions like sum and products of continuous function, and they are all again continuous functions. And why we say that it is a beautiful, it has the intermediate value theorem or a property that if the limit is put inside the sequence of functions, and the limit can be put inside the function as a limit of functions. In topology, the continuous functions are exactly functions which preserve topological structures. And why we study continuous functions? Why these functions are studied? If a function has a derivative, then it is continuous and thus continuous, underlining every problem involving differentiation. Continuous is studied, continuity of functions is studied in every problem where the differentiation is involved. Because every continuous function or every differentiable function is continuous, by that we say that whatever the problem we are dealing with, the differentiation and it has the continuity of functions. The ability to predict the world around us can be modeled by differential equations, and you can't solve any differential equation without continuous function. And that is the main reason that we study continuous functions. They're used in wide variety of disciplines from biology, economics, physics, chemistry, and engineering, whatever not. In every discipline, you are going to use the continuity of functions or differentiability of functions. They can describe exponential growth and a decay, the population growth of species, or change in the investment return over time. And wherever the differentiation comes into the picture, you are going to use a continuity of a function, and we study the continuity of functions. But for some models that are not continuous, for example, I give an example, and they again can be explored to a continuous function. For example, if a call center is counting the number of phone-ins they get each minute, and this is an integer valued function and does not make any sense for that to be continuous function. And a person is recording a number of phone-ins or phone calls for each minute. And because that it is an integer type, and you cannot just say that it is continuous, but you can interpret, you can explore that into the data, and you just have a grid of, you can interpolate with a continuous function and then apply the methods of calculus. And whatever the dots you are getting for each minute, and you can approximate that dots into a function, and the function is nothing but a continuous function. And then again, we can apply whatever the methods we are going to use in the calculus to those functions. And this is one of the example where the continuous study, though the call recordings, they are not approximated to a continuous function, but they can be approximated to a continuous function, and then we can study the properties of continuous functions. Another application for continuing study of continuity functions is integration, and which works for all continuous function. And we also know that every integrable function is a continuous function, and that is why we study a continuous function. So anytime you want to integrate something, you are better be working with a continuous function. So whatever the problems you are involving to integrate, to differentiate, you are working with continuous functions. Since integrals are used for everything from mechanics to medical imaging to deep learning, that is an essential tool from calculus that you pretty must need continuous functions to use effectively. So whatever the problem you are using, it may be in medical sciences, it may be in mechanics, it may be in computer science, or whatever the problem you are studying on, they use the functions, and all the functions, they are continuous function. And as an example, the area between curves, the distance between 2 points, or the velocity, acceleration, volume, average value of a function, work, probability, surface area, and all these problems, they are all involved in the continuity of functions or continuous functions. And these are again some of the examples: modeling and simulation of systems that change with time, and because change with time always has the differentiation, and it is again a continuous function, and such as flight of aeroplanes, and again can be modeled as a continuous functions. The satellites, planets, etc., the motion of the satellites, planets, and so on, they all study, and they are concerned with the functions, and they are all functions of continuous type. The physical equations such as Newton's laws of motions, Einstein's general relativity, law of relativity, Maxwell's equations for electrodynamics are naturally expressed in calculus. They are all of continuous functions. And these are the studies where, these are the areas where we study about the continuous function. And why we study continuous functions. And these are the applications where we study the continuity of the functions. Differential equations, you can see the first example, dp by dh, and it is minus kt mb mg by kt, where ph is p naught e to the power of minus mgh by kt. You are studying the atmospheric pressure variation with height h, and it is a differentiable equation problem. And because that equation always includes a function, and this function is always a continuous function. In real-time applications, you can go for any differential equation, and that differential equations involve the problems involving the continuous functions. And applications to partial differential equations and the population growth problems and the dynamic infectious diseases, solving complex force in physics, the signal processing, they're all involved with continuous functions. And in biology, you can go for the continuous problems. In software or machine learning, you can go continuity of functions. And some applications of continuity functions. And I give some examples where we can go for the continuous. Suppose that your account is initially 10,000 rupees in it. The account pays 5% annual income compounded monthly. Is it continuous? Sketch the graph of your balance as a function of time. Sketch the graph of population of Earth as a function of time. Is this a continuous function? Why is it reasonable to represent this graph as a continuous function? Or sketch a graph of your telephone cost for using phone. Is this a continuous function? And whatever the problems, and here is an interesting problem again. The sketch the graph of your blood pressure as a function of time while a bicycle ride. Is it a continuous function? And these all are the applications in real-time applications of continuous problems. Generally, we do cross all kinds of these continuous functions, but we function or it is a differentiable equation and so on. And as I am given a continuous, the first example was if he had an initial amount of 10,000 rupees, he has invested in a bank with an interest of 5 rupees per year or 5% per year over a time of t. And this can be approximated to a function of this form p into e to the power of rt. And it is an exponential function and it is always a continuous function. And in this case, it can be approximated to a continuous function and use all the properties what we have in continuity, and we can predict the value of the, we can predict or you can estimate any value, or we can also find the rate of change of that particular values over the time of period. And second, we were counting upon the population growth, and it again can be approximated to a population growth problem and so on. And this is the other example. The third example, it was this problem. The sketch a graph of a blood pressure as a function of time while you are riding a bicycle. Is it a continuous function? And for that, I have drawn a graph, and this, the blue lines indicates that it is the person who is riding bicycle is at rest, and then red indicates that it is having some blood pressure, and the green line indicates that he is under low blood pressure. And at different time slots, we have measured all the quantities, and we say that it is always the low blood pressure is with green lines, and then blue with at a normal time, and then red with high blood pressure. And this again can be approximated to a continuous function. And whatever the properties, at a particular time, you can calculate the blood pressure of that person who is riding bicycle, and whether he is having a low blood pressure or a high blood pressure, and what is the rate at which the blood has pumping, or what is the other consequences is going to get, and after the study of these terms. And this is an example of comparing the stock exchange and so on. And these are some of the applications where we do come across in our daily life, but always we try to neglect those things, but those are always the continuous functions. And these are Bernard Bolzano, and they had a contribution towards the continuity of functions. And epsilon delta definition was given by Bolzano. And then this is Scotches, and they have extremely worked on the continuity of functions. And this is an example, and where I give that the illiterates of the 21st century will not be those who cannot read and write, but those who cannot learn or unlearn and relearn. And as this pandemic situation, we are in a period where we need to advance into our technologies, and the person who is teaching the Reliances for last 10 years, and if he is not updating himself, and he will be an unlearn, because he has whatever the contents he had, he's putting all the for last 10 years he's putting all the terms as again and again, and he's not learning in an advance where the technology is advancing, and those are considered to be the illiterates. The illiterates of the 21st century will not be those who cannot read and write. Who cannot read and write, they are not illiterates, but those who are not learning and relearning, and they are adopting only what they are having, are said to be the illiterates. And coming to the definition of a limit, we say that the limit of a function f of x as x approaches to a is L, and we write it as x tends to a, limit x tends to a, f of x equals to L. As x approaches to a, the function f of x, and this is your function f of x, it tends to f of a, or it tends to L, and that is what we mean by the limit of a function f of x. And this is limit x tends to -2, where f of x is given as -3x, and if x not equals to -2 and equals to 1, x equals to -2. And this is a function where f of x is f of x equals to 3x is defined as -3x is defined as, and at x equals to -2 and x equals to -2, it is 1, and limit x tends to -2 f of x, and this is x tends to -2 -3x, -3 into limit x tends to, and this will be 6. It is 6 at x equals to, at x not equals to -2, and at x equals to 2 -2, it is 1. Therefore, f of -2 is 1 and is not involved. Why it is not involved? In the sense, f of -2, we are approximating it to f of -2. F of -2 is 1, but as x tends to -2, as x approaches to -2, it is 6, not 2, not 1. And we give epsilon definition of a limit. We say that x tends to a, f of x equals to L, if and only if a given positive number epsilon, you are given any epsilon 0.5, there exists a positive number delta, it may be 0.2, such that if x minus a, whatever x in between a minus delta and a plus delta, whatever x in between a minus delta and a plus delta, and f of x minus L, whatever may be your f of x in between L minus epsilon and L plus epsilon, and it is less than epsilon. It is less than epsilon. Therefore, we say that the limit of a function f of x, x tends to a, f of x tends to L, if for any epsilon greater than 0, there exists a delta greater than 0, such that modulus of x minus a less than delta, 0 less than delta, then f of x minus L is less than epsilon. This means that if you are given a small interval L minus epsilon and L plus epsilon centered at L, we can find a small interval a minus delta and a plus delta, such that for all x not equals to a, in between a minus delta and a plus delta, f of x is always in between L minus a and. You are given any a, every x in between a minus delta and a plus delta, you can find L where f of x minus L in between L minus delta and L plus delta is always lying in between those values. And if it's satisfying this condition, we say that it is an epsilon definition for, and it is epsilon delta definition. And this is an example where we show that the limit extends to 2, 3x plus 4 and equals to 10. Let epsilon be greater than 0 be given. We need to find a delta such that modulus of x minus 2 is less than delta. And therefore, modulus of f of x minus L, f of x is 3x plus 4 and L is 10. It is less than epsilon, but 3x minus 4, it can be written as, and delta, which is expressed in terms of epsilon, and epsilon by 3 is your delta. Therefore, x minus 2 is less than epsilon by 3. And next example, it is show that a limit extends to 1 by x equals to 1. And the same example, let epsilon be greater than be 0 given. We need to find a delta such that modulus of x minus 1 is less than delta. Then f of x minus L is less than epsilon. And f of x minus 1 is less than epsilon implies that it is modulus of x minus 1 by x, and it is 1 by x, and this is, and 1 by x is because that it is always less than 1. And we say that it is x is less than 1, and mod x minus 1 is less than 1 by 2, then x in between 1 by 2 and 3 by 2. And thus 1 by x, x minus a, mod x minus a is 1 by x mod x minus a, and it is 2 into modulus x minus a, and we take the minimum of epsilon by 3 and 1 by 2, and this gives the delta value, and it says the properties that modulus of x minus a is less than delta, implies that modulus of f of x minus L is less than epsilon. And definition in continuous in terms of functions, continuity in terms of limits of function. A function f is said to be continuous at a point x equals to a if the following are true. And what I mean by that, it must satisfy all the three properties. F of a must be defined, and then limit extends to a, f of x exists, and limit extends to a, f of x equals to f of a. And if it satisfies all the three properties, then we say that a function is continuous at that particular point x equals to a. We say that a function f of x is continuous at a point a if f of a is defined. This is your f of a. It must be defined, and limit extends to a, limit extends to a, f of x exists. This is your f of x exists, and limit extends to a, f of x equals to f of a. And definition in terms of limits of sequences, and limits in terms of limits of sequences also, you can define the continuity of function. Let f maps S to R be any function with S contained in R, and let x naught belongs to S. The function f is said to be continuous at x naught if whenever the sequence xn converges to x naught in S, the sequence f of xn should converge to f of x naught in R. That is, limit n tends to n, f of xn equals to f of x naught. And whenever limit n tends to infinite, xn equals to x naught. A function f is said to be continuous on R if it is continuous at every point on S. If the function f is not continuous at a point, then we say that it is not continuous. So in terms of sequences, a sequence xn is said to be continuous when limit n tends to infinite, f of xn equals to f of x naught, and it is continuous at f x naught. And definition in terms of, we have the sequence, the cos x sequence, and it is pictorially represented, and these sequences converges, and minus sin x by x, the sequence converges. The sequence converges, or we say that the limit of that particular sequence converges to a point when it is limit n tends to infinite, f of xn equals to f of x naught. And a limit, the continuity in terms of the neighborhoods. A function f is continuous at a point if the range of f over the neighborhood of C sinks to a single point f of C, as the width of the neighborhood around C sinks to 0. More precisely, a function f is continuous at a point C of its domain. For every neighborhood n2 of C, there exists a neighborhood n1 of f of C in its domain. F of x belongs to n1 f of C, that whatever x belongs to n2 of C. You can represent this as we say that f is continuous at a point in terms of neighborhoods. You are defining if x is a point and then its range is defined as f of x. The neighborhood of x is defined as u, u, and if in every neighborhood of x, you can define a mapping some f of u, and if f of u also have a neighborhood, then we say that f of x, that function f of x to y is continuous at a particular point x. And in terms of neighborhood also, you can define the same thing we have. If the image of x is continuous, then we say that it is continuous at that particular point. And in terms of metric spaces also, you can define the continuity of functions. If two metric spaces x dx and y dx, and there is a function f map x to y, then f is said to be continuous at a point c in x. If for any positive real number epsilon, there exists a positive number delta, such that all x in x satisfying dx is less than delta will satisfy the images. If the same graph I am going to use in metric spaces also, if the modulus of, I say that the metric space x to y, a function x to y, two metric spaces with distance properties dx and dy, if there is a point x in x and the image of x is f of x, and if the distance between any 2 points, the neighborhood points of x, and if f of x neighborhoods, if they are again continuous, we say that it is continuous in metric spaces. And in functional also we define the same thing. And here it is an example, the functions f of x, where it is discontinuous. You are given a function f of x equals to x plus 2. It is continuous everywhere, and limit extends to a, x plus 2 is a plus 2, and the limit extends to a f of x equals to f of a. The property is that function is continuous is f of a must be defined, and then limit extends to f of x must be f of a, and it must be continuous everywhere. And if I go for the second example, g of x is x square minus 9 by x plus 3. It is continuous everywhere at x except at x equals to minus 3. G of 3 is not defined. Minus 3 is not defined. Therefore, it is not continuous, discontinuous function. The third example may be h of x equals x plus 2 if x greater than 1. And this is your 1. If x greater than 1, it is x plus 2, straight line, and x equals to 1 if x less than or equals to x equals h of x equals to 1 if x less than 1. But limit extends to 1 minus it is 1, and limit extends to 1 plus h of x is 3. But at x equals to 1, it is not continuous. Therefore, we say that h is not continuous at x equals to 1, or h is continuous everywhere except at x equals to 1. And f of x equals to minus 1, x less than or equals to 0, and 1 if x greater than, and it is not continuous at x equals to 1. 0 minus you can define a continuous function, 0 plus you can define a continuous function, but at x equals to 1 and limit extends to a, f of is not equal to f of 1. Therefore, it is not continuous. And continuity at a point, if that point is an interior point, we say that f of x is continuous at the point if it is an interior point when f of a equals to limit extends to a f of x. And for the continuity test, we go for f of a must be defined and limit extends to a f of x must exist, and f of a equals to voice లేదా
వస్తుంది సార్.
వస్తుంది సార్.
క్లియర్ గా ఉంది సార్. వస్తుంది సార్.
It's clear, sir. Continue. Please continue. It's clear.
Okay. Continuity at x equals to minus 1, and I can give the 3 properties for continuity test. You are going to find that f of a must be defined. F of minus 1 is minus 1. Limit extends to minus 1, f of x is 1, and it must exist, and limit extends to minus 1, f of x equals to f of minus 1. Therefore, we say that f of x is continuous at x equals to minus 1. And if a function, if a function which satisfies these three properties, we say that it is continuous. And at x equals to, and this is a graphical representation of a graph of that particular graph. I'm using the same example and study the continuity at x equals to -4. F of 4 is what is your f of x? And here, this example is given with the graph. With the graph, I'm showing that it is discontinued at x equals to 4. And this, there is no point at x equals to 4. This represents a dot, which is not blocked. And this represents at x equals to 4. This is not defined. But at x equals to 2 is defined. And x equals to -2 is not defined. I define at x equals to 4. Using the graph, I say that whether it is continuous or not. F of 4 is not defined, and limit extends to extends to 4 f of x. Towards the left side, right side, it is f existing, and f of 4 equals to limit extends to 4 f of x. Therefore, it is not continuous, but because f of 4 is not defined, and you can not say that it is a continuous function. The same example only we are taking, and this is a problem where f of 2 can be defined. F of 2 is your this dot line. F of 2 is defined, but limit extends to 2 f of x. Limit extends to 2 f of x. Limit extends to 2 minus and limit extends to 2 plus. And because they are different and this is not defined, and f of 2 is limit extends to 2 f of x. And therefore, again, this is not continuous at x equals to 2. The same example using the graph only, I'm showing that f of -2 is defined. F of -2, sorry, there is a correction. F of 2 is defined. F of extends to 2 minus 2. F of x is defined. And then this is a small confusion. I'll skip this. And to check whether it is continuous at the endpoints. Continuity at endpoints. A function f of x is continuous at the endpoint a if limit extends to a plus f of x and limit extends to a minus f of x equals to f of a. We say that a function f of x is continuous at the endpoints. If x is your a, x is your 2, a point, we say that it is continuous towards the right hand and towards the left hand, or towards 2 plus and 2 minus accordingly. And continuity from the right hand, it is limit extends to a plus, f of a must be defined. Limit extends to a minus f of x must exist, and f of a must be limit extends to a minus f of x. And continuity at the right hand, same, f of a must be defined. Limit extends to a f of x must exist, and f of a equals to limit extends to a plus f of x. And these are the properties, and towards the right hand and the left hand, we must define a minus and a plus. And these are the types of discontinuities. You are given some functions, it may be a function taking this particular graph, and I say that it is a continuous function, and this is your continuous function. But at x equals to -2, only at x equals to -2, this is x equals to f of x is 2. At x equals to -2, f of x is 2. Therefore, if I neglect only this particular term x equals to -2, and other case, in any other case, the function is continuous. In any other case, the function is continuous except at x equals to -2. And if I neglect that particular term, that particular point x equals to -2, it is continuous. Such type of continuous functions, such kind of discontinuity is what we mean by removable discontinuity. If I remove that particular point, you can find that it is continuous function. And I have the same function, and I have the same function towards the left of the origin, towards the negative axis. and this function is discontinuous to infinity. And at x equals to some point 0, you cannot define that particular function. Therefore, we say that it is of point of infinite discontinuity. And I have the other example towards the positive axis, and at x equals to 2, I have at x equals to 2, it is continuous, but at x equals to 2 only, the function is jumping, and that particular function, whether it is jumping, and that is what we mean by jump discontinuity. And these are the conditions what we use for the discontinuity of functions. And these are some of the examples where we define the continuity of functions, and you can solve these functions. And the fundamental theorem for the continuous functions: if f maps S to R be a function with domain f and S contained in R, that x0 belongs to S, then f is continuous at x0 if and only if for every epsilon greater than 0, there exists a delta greater than 0 such that f of x minus f of x0 less than epsilon whenever modulus of x minus x0 less than delta for every x belongs to S. And this you can prove. And then there is nothing very much hard to prove this theorem. The necessary part that let f is a continuous function. Let f be a continuous function at x0. Suppose that f does not satisfy the given condition. That is, we use the quantifiers, and the quantifiers, the change accordingly. For every epsilon greater than 0, there exists a delta greater than 0, modulus of f of x minus f of x0 less than epsilon whenever is not satisfied. And we change the quantifiers. For every, we use that there exists an epsilon, and for every there exists a delta, we use for every delta greater than 0 implies that. And this you can prove. And coming to algebra of functions, if f and g are any two continuous functions at a point x belongs to R, then we can show that f plus g is continuous, f minus g is continuous, f into g is continuous, provided that g of x is not 0, and f by g is continuous, and kf is continuous. And k is any constant which is belonging to the real numbers. And all these functions, they are continuous functions, and you can use the algebra of continuous functions, whatever the properties we have used, such as a plus f plus g, f minus g, f by g, and so on. And you can apply all those to these kind of functions. All the polynomials, they can define that they are continuous functions. Rational functions, they are continuous functions. Root functions, they are continuous functions. Trigonometric functions, inverse trigonometric functions, exponential logarithm functions, they are all continuous functions in their domains, whatever the domain you are given, and you can define that they are continuous functions. And you have the other theorem also. These theorems, I'm not stressing on the theorems. I'm mainly focusing on the graphical representation of the problems what we have. And if f is a function, real valued function, continuous at a point x0 of the domain f, then modulus of f is also continuous at that particular point. And this is one more theorem, the compound function. If f is continuous at a point x0 and g is continuous at x0, then the composite function g of f is also continuous at x0. And we use the limit definition, limit of a sequence definition, and find that they are continuous. And this is one of your example to show that modulus of x is continuous function on R. And this is an example where f of x equals to 2x squared plus 1, and prove that it is continuous using epsilon definition. And don't get confused with your epsilon definition. And this is as simple as that. And using limit concept, I am proving that it is limit xn tends to limit xn equals to x0, and consider limit of f of xn, and this is therefore it converges, and therefore we say that it is f of x is continuous. And inverse functions and continuity. The inverse function of any continuous is 1-1 function of any 1-1 function is also continuous. And this function, if I take the inverse of that particular function, and if this function is continuous, we say that the inverse function is also continuous. The same, it is a replicate only that it is the change in the orientation, and therefore if this function is continuous except at the points minus pi by 2 and the pi and so on, we say that it is continuous, and the inverse functions also are also continuous. And one of the basic principle of the continuity of functions is the intermediate value theorem. What the intermediate value theorem states is, if f is a continuous real valued function on an interval, if f of x is continuous on a real on an interval I, on an interval y, then f has an intermediate value property on I. That is, whenever a comma b belongs to I, and a less than b, and y lies between f of a and f of b, then there exists at least one x belongs to, then there exists at least one c belongs to this open interval a comma b, such that f of x equals to 1, such that f of c equals to y naught. And that is what we mean by intermediate value theorem, and it's widely used in finding the solutions of the problem. And these are the other representations. You can represent that in any other form. If you are defining a function f of x on the closing on an interval, and if a and b are any 2 points, and there always exists a point c such that f of c equals to y naught, or y equals to f of x, you can find but that particular c. You can use that for any points. And if C1, C2, Cn, they are intermediate points also, you can apply this intermediate value theorem and find that particular C1, C2, Cn, where f of C1, f of C2, and f of Cn, they are approximated to y naught or y in that case. And these are again some of the examples. An intermediate value theorem says that f of x is continuous on closed interval a comma b, and you can always find a y naught between f of a and b. Then there exists at least one c belongs to, this is open interval a comma b, such that f of c equals to y naught. And they are all satisfying the same properties. If a and b are any two, if it is closed, f of x is defined on the closed interval a comma b, then always you can find a c such that f of c equals to y naught. And in this case also you can find any value such that f of c equals to y naught. And finding the roots, the consequence of intermediate value theorem is nothing but finding the solution of the problem. You are given any function f of x is some property, and in between minus and between 1 and in between 1 and 2 you can find a solution, and there exists at least one c belongs to open interval a comma b, such that I can picturize that it is in between 1 and 2. They're always between 1 and 2. You can find a solution, and this is the solution you can find. Interval theorem prove the solution of the problem. You are given any function, and for that particular function you are defining f of at x equals to minus 1, it is 1, and at x equals to 0, it is 1. F of 0 is 1. Minus 1 is 1. And this is some, f of 0 is minus 1. This is some mistake is there. And then you can find some x between minus 1 and 0 by intermediate value theorem. And use the same function. You are given any two functions also, you can find a solution that for that. And if f of x equals to g of x, then there is a solution. And h of x, I write it as the difference between two polynomials as algebra of polynomials, f of x minus g of x. And then we can find h of x. And you can find the continuity in between 1 and 2. And h of 1 is minus 1 and h of 2 is 12. And if it is having the opposite signs, then it exists at least one c between a and b, one c in between 1 and 2, such that f of x naught equals to y naught. And this is h of c equals to 0. And you can approximate that h of x and f of x and g of x are same. And always that you need to be in advance, you must be updated Otherwise, you are outdated and you cannot justify what the content you have. And in research publications also these kind of continuous functions are used. And this I've picked as an example where the research is going on or a research problem is taken from. And he has defined a continuity as, in one of your research problem, I have taken an example where in one of your research problem, he has taken or he have defined a continuous function as, let a program P have the specification S. Let a program P have a specification S, and P is a failure continuous. P is failure continuous at x naught if and only if there exists B greater than 0, such that if P of x naught not equals to S of x naught for every t belongs to modulus of x minus t is less than P of t not equals to S of t. What I define the system fails is, whenever you are running a program, an algorithm can be defined as a sequence of steps to solve a given problem. And if a problem, if that particular algorithm has 10 steps, and if it is not continuous at the 7th step, and what I mean by it is not continuous at the 7th step is if the 6th step and the 8th step, I'm calculating the continuity of that particular program at the 7th step. And if it is not continuous at the 6th step and the 8th step, we say that the algorithm is not correct. The algorithm is not correct. And what I mean by that is x minus delta and x plus delta in the range of x minus delta, in the range of 7 minus 6 and 7, in the range of 7 minus 1 and 7 plus 1, x minus delta and x plus delta, if it is considered to be a sequence of only one step, and if the system fails or if the program fails at the 7th step, and if it is not correct at the 6th step and the 8th step, we say that the entire program is wrong or entire program is not correct. And that is what we mean by in terms of continuity. And the same definition he has given in terms of the continuity of the function. That is, if the program fails to meet its specifications at some input, then it is also failing in the neighborhood. It fails to meet the specifications at some point. The some point may be your 7th point. If it is not satisfying in the neighborhood points, and the neighborhood in this case is your 6th point and the 8th point, and if the system is failing and if the program is failing at that particular point, then the program fails for every neighborhood. And that is what we mean by the continuity of the functions. And next, I am going to have a discussion on uniform continuity of the functions. A function f maps d to r is said to be continuous on D. It is required that for every epsilon, for every x naught belongs to D, and for every epsilon greater than 0, there exists a delta greater than 0, such that modulus of f of x minus f of x naught less than epsilon whenever modulus of x minus x naught less than delta. And this is the definition for the continuity of the function. And note that whenever we go for the uniform continuity, only the quantified matters. And in this case, the quantifiers are for every and there exists. For every epsilon greater than 0, for every epsilon greater than 0, and there exists a delta greater than 0. And coming to proving that they are not continuous or they are uniform continuous, it happens that for every epsilon greater than 0, there exists a delta greater than 0 that works for all x naught in D. Then f is said to be uniformly continuous. Then f is said to be uniformly continuous. Suppose that you are taking some function f of x equals to x, f of x equals to x, and epsilon equals to 0.5 and 0.2, delta equals to 0.2. And this may be your function f of x equals to x, at a particular point, and this may be your x equals to 1 in the neighborhood of this, and this is your x minus delta and x plus delta, and this may be your f of x plus epsilon and f of x and f of x minus epsilon. And I take epsilon equals to 0.5 and delta equals to 0.2. You are fixing delta as delta is this range and this is your 0.2. And x naught may be any point. X naught may be any point. This delta equals to 0.2 does not change. This delta equals to 0.2 does not change. And f of x minus, accordingly, f of x plus epsilon and f of x minus epsilon may be changing, but this delta does not change. So for any epsilon greater than 0, there exists a delta greater than 0, such that modulus of f of x minus a is less than delta, or x naught less than delta, and f of x modulus of f of x minus the f of a is less than epsilon. And that is what we mean by x naught is less than epsilon. That is what we mean by continuity of function. I give the same example when we go for the uniform continuity of the function. I take this example, and this may be your function, some y equals to f of x, and this is your x square. Index, and I take epsilon equals to same 0.5 and delta equals to 0.2. And suppose I try to take. And for small x naught, if I take delta equals to 2, delta equals to 0.2, and this is x naught minus delta and x naught plus delta, and this is your delta. For smaller values of x, I'll take 0. For smaller values of x, and for fixing epsilon equals to 0.5, for 0.5, and for larger values of x naught, and the delta may be small. And here the delta is very large for the smaller values of x, and delta will be small. So you cannot define a fixed value for delta where f of x minus f of x naught is less than delta and f of x minus f of x naught less than epsilon. And that is where we have the uniform continuity. And if a function f of x is said to be continuous, if at every point you can define such delta where modulus of x minus x naught is less than delta and modulus of f of x minus f of x naught is less than epsilon. For every x minus x naught, you can define a delta, and that is what we mean by the uniform continuity of a function. Thus, we define the uniform continuity of a function as if for every epsilon greater than 0, there exists a delta greater than 0, such that f of x minus f of y is less than epsilon whenever modulus of x minus y is less than delta. That is, for any in between, there exists any x and y, such that the distance between those 2 points is always less than delta, and that is what we mean by uniform continuity of functions. The only difference between these two definitions is the order of quantifiers, and what I mean by quantifiers is for every, there exists, and so on. And we can prove that f is continuous, and the proof will be of this form. Choose any x naught belongs to S, and choose any delta greater than epsilon greater than 0, and delta is always in between. Delta is always depending on x naught and epsilon. In the previous example, we have shown that f of x equals to x, where it is not depending on x naught, it is only depending on the delta. Though you are varying though you are varying some x naught point, it is not depending on the x naught. It is only depending on the width of that particular interval, x minus delta and x plus delta. It is independent. But if I take the other example, some f of x equals to x square, which is depending on both x naught and delta, and that is what we mean by the continuity of function. And if it is depending on only the delta, epsilon, we say that it is uniform continuous. The expression for delta equals to delta of x naught and epsilon can involve both x naught and epsilon, but must be independent of x. And that is what we mean by the continuity of function. And uniformly continuous is where the delta is always expressed in terms of epsilon. And that is what that is only the major difference between a continuous function and a uniformly continuous function. And this is the same what I have explained, which is not uniformly continuous, because and this is a function f of x equals to x square, and given a point x1 which is close to 0, epsilon neighborhood is about f of x1, and required delta can be fairly very large. And this is your delta area, which is very large. But as x increases, the value of delta decreases. This means that continuity is not uniform. It is not uniform throughout. Therefore, we say that it is not continuous. And this is shown graphically, that if I define delta in this case, this is very large, and I'm fixing that particular epsilon. Epsilon may be 0.5 in this case. At that particular point, f of x1 minus epsilon, f of x plus epsilon, f of x2 minus epsilon, f of x2 plus epsilon. But at this particular point x1, this x1 minus delta may be large when compared to x2 minus delta and x2 plus delta. Therefore, it is not uniform throughout. We say that it is not uniformly continuous. And this is an example where we can see that the horizontal line, it represents the width of your delta, and vertical line, that it represents your epsilon. It represents the width of your delta, and this represents, the vertical line represents that it is the width of your epsilon, and this must be constant throughout. It must be constant throughout, and that what we mean by the function f of x is uniformly continuous. This blue line indicates that the function is 1 by x, and the red line indicates that it is under root x, and they are uniformly continuous because at every point that is continuous. In the same example, you can extend that, and this delta must be fixed for any value of x throughout your interval, and f of x minus f of x1 minus f of x2, or f of x minus f of y must be less than epsilon, and here x1 minus x2 or x minus y is less than delta in that case. And this is an example to show that f of x equals to 3x is uniformly continuous. For any given epsilon greater than 0, there exists a delta greater than 0 again. And to make f of x minus by taking x sufficiently close to y, what I mean by sufficiently close to y, it must be less than delta. F of x minus f of y equals to 3x, and 3 into x minus 1. In this case, I take delta equals to epsilon by 3, and then it satisfies the property. And the same, another example, if we choose, and then modulus of f of x minus f of x naught, and this is again 3 into, and delta is again epsilon by 3. And this is your third example, and 0 and 4, and f of x is given as x square, then f is not uniformly continuous on R. F is uniformly continuous on S. Let epsilon be given, and delta equals to delta by 8, and x naught equals to, and choose x naught equals to. X naught is in between 0 and 4, x is in between 0 and 4, but x naught plus x is in between 0 and 8. Modulus of x minus x naught is less than delta, and modulus of f of x minus f of x naught is epsilon by 8. Delta is expressed in terms of delta by, sorry, here it is a change. So it is not delta by 8, it is epsilon by 8. and therefore modulus of f of x minus f of x2 is less than or equals to some m into. By this you can have before examples you can see that, and whatever the examples we have seen, and from this example we have seen that f of x minus f of x naught is expressed in terms of 3 into modulus of x minus x naught. In the second example, we have seen that it is f of x naught minus f of xn is represented as some 8 into modulus of x minus x naught, which has a property that in the preceding examples or the proofs, f satisfies the inequality of the form modulus of f of x1 minus f of x2 is less than or equals to m into modulus of x1 minus x2. And this property is what we mean by Lipschitz inequality. And whatever the m we have, epsilon by 8 and then epsilon by 3 and epsilon by 2 and so on, whatever that we had, that constant is always said to be the Lipschitz constant. And that is your theorem. If f satisfies f of x1 minus f of x2 less than, then it is uniformly continuous. So for every epsilon greater than 0, I choose delta to be epsilon by m. And then modulus of f of x minus f of x naught is nothing but m into x minus x naught, and that it is less than epsilon, then it completes your proof. And this is again an example where it is not uniformly continuous. And the same example in other form. And I take x equals to 1 by delta and y equals to 1 by delta plus delta by 2. Modulus of x minus it satisfying that particular property, but modulus of f of x minus f of y is x plus y into x minus y, and this is equal to 1, which does not satisfy. So proving that it is not uniformly continuous is modulus of f of x minus f of y is greater than or equals to epsilon. And here I have taken epsilon equals to 1, but we need to get that it is less than 1, but it is greater than or equals to 1. Therefore, it is not uniformly continuous. The same example in other form, in the bounded set I have taken. If it is in a bounded form, then modulus of x plus y is always less than or equals to 6. And for any epsilon greater than 0, I have taken some epsilon by 6, and modulus of x minus y is less than delta. By definition, modulus of f of x minus f of y is 6 into and equals to epsilon. And therefore, it is uniformly. Modulus of f of x minus f of y is less than epsilon, and delta is nothing but epsilon by 6. We say that it is uniformly continuous. Bounded set, it is continued. And which leads to the other theorem that if it is bounded set, then it is continuous. If f is continuous on a closed interval a comma b. This example was if f of x is continuous on closed interval. We say that f of x is continuous on closed interval a comma b. If it is continuous on closed interval a comma b, you can say that it is uniformly continuous on closed interval a comma b. And this theorem is proved using Bolzano-Weierstrass theorem, and that can be proved. And how this sequence is related to uniform continuity. Recall that the continuous image of a convergent sequence need not be convergent if the limit of the sequence is not in the domain of the function. Example I take, f of x equals to 1 by x and xn equals to 1 by n. Sequence xn converges to 0. The sequence xn, this sequence f of x, this converges to 0. But f of xn equals to n. But limit n tends to infinite, f of xn equals to n for all n. Thus the sequence f of xn diverges to plus infinity, because f of xn equals to limit n tends to infinite, f of xn equals to n, and this tends to infinity, therefore the sequence. But with uniform continuity, you have the following. If f maps d to r is uniformly continuous, and suppose that the sequence is a Cauchy sequence, then f of xn is a Cauchy sequence. And the bounded open interval, determine the function uniformly on a bounded interval. Bounded open interval. Bounded interval, it is bounded open interval also it is uniformly continuous. I'll stop here. Okay, I'll stop here. Thank you for your patience listening. And I request any doubts or any suggestions from the audience.
Dear participants, if you have any questions, you can ask now one by one, or you can post your queries in the chat box. It's better to post in the chat box. We can read those questions for the resource person.
I'll be answering all the things, and if you post, I can answer that.
Yes.
Any doubts you can ask.
Yes. Yes, you can ask the questions directly. Okay. Meanwhile, I would like to say some things about our resource person. Thank you, sir. Thank you very much for sharing your insights on the application of continuous functions. And you mentioned some contributions of Bolzano, Bernard, and Augustine Lewis. It was interesting. And I found a thought-provoking quote in your presentation. The illiterate of the 21st century will not be those who cannot read and write, but those who cannot learn, unlearn, and relearn. It was very interesting. So we have to learn to shape our future. Your future depends on what you are learning and how you are learning. Thank you for thank you for such an interesting session, sir. So shall we move to the next session? Sambashwara sir. Okay, madam. Okay, right. Next, we look forward for the presence of Dr. Rayaprolu Bharavi Sharma, Assistant Professor of Mathematics, Kakatiya University, Warangal. So now on the topic differentiation and mean values theorems. Now I request our Assistant Professor of Mathematics, Srimati Anuradha Madam, to say some interesting facts about our resource person. Ma'am, over to you.
Good morning, everyone. Thank you for being here with us this morning. I feel privileged to introduce our today's resource person, Dr. Rayaprolu Bharavi Sharma, in this webinar. Dr. Bharavi Sharma is an assistant professor of mathematics, AU Kakatiya University, Warangal. He was educated in Warangal. He has teaching experience of 26 years and research experience of 14 years. He was awarded PhD under the supervision of Professor T. Ram Reddy, and his research area is complex analysis. He has published 65 papers in national and international journals, and he has presented 30 papers in various national and international conferences. He has completed a major research project sponsored by UGC and 5 short-term courses and 5 FDPs. Moreover, he awarded Best Teacher Award twice and Best Researcher Award. He published many books for Kalyani and Eschan publications. He has guided 3 PhD students, and present 4 students are pursuing their PhD and 3 students have submitted their thesis under his supervision. He is a member of 4 professional bodies, a member in BOS, DRC, DC in 4 institutions. He has organized many workshops and training programs. Moreover, participated as an organizing member in 10 programs. He is a nodal officer for Kakatiya University and Swayam coordinator also. With this brief introduction, I request Mr. Bharavi Sharma to share his ideas on differentiation and mean value theorems. Thank you, sir, for accepting our invitation and about to share your expert opinion with all the participants gathered here. Thank you. Over to you, sir.
Yeah, good morning, one and all. This is Bharavi Sharma interacting with you people. A warm good morning to all of you. And first of all, I would like to congratulate the principal, Sri Ratna Prasad Garu, faculty members of the department, head of the department, Sambashivara Garu, coordinator K. Srinivas Garu, and members of this organizing committee, Venkateshwara Garu, Jyotirmay Garu, Anuradha Garu, Saroja Garu, Nagarekha Rani Garu, and the IQAC coordinator, madam. I thank all of you and congratulate all of you for conducting such a wonderful program on a favorite topic of mathematics, that is real analysis. Concepts of real analysis, that is the title of today's webinar. So my topic, I also congratulate my earlier speaker and my brother, Dr. L.P. Rajkumar, for having presented nicely, showing a lot of graphs about continuity, uniform continuity and all that. Now it is my turn to speak about differentiation and mean value theorems. So am I audible?
Yes, sir, audible.
Yeah, okay. Then,
Clear.
Okay. Then let me start this presentation. Yeah. So now the concepts on real analysis. The topic of my talk is about differentiation and mean value theorems. Differentiation and mean value theorems. So I have given my mail ID here, rbsharma005@gmail.com, and I have given my numbers also. People who are having doubts in analysis, any part of analysis in algebra, in abstract papers, can approach me on these numbers and they can ask me doubts through this mail ID. And the first number 9849550271 is my mobile number for which there is WhatsApp connection. So you can also send your queries to this number. So now I start my presentation with by showing two slides here. One is these are my parents who are my first teachers in the life and also in the career. And then my Guru Professor T. Ram Reddy, who is my research supervisor. And because of him, I'm here in the university today. I'm able to give some lectures like this before you. It is only because of him. Now, these are the contents of my talk. Basic properties of the derivative, relation between differentiability and continuity, algebra of differentiable functions, examples, mean value theorem, then Rolle's theorem, Lagrange's mean value theorem, increasing and decreasing functions, examples, and generalized mean value theorem or Cauchy's mean value theorem. So before I start the first topic, let me tell you about what is differentiation. See, if you take the branch of calculus, derivative, differentiation, and integration are the two major branches of calculus, which we have been studying from the school level, and in particular in intermediate first year and second year, people have studied, all the teachers, all of us have studied differentiation and integration when we were in intermediate level. Now, these two are the main branches of calculus, and because of this differentiation and integration, so many other branches of mathematics have been derived, in particular differential equations, partial differential equations, and so many other branches. In fact, real analysis also in our FDP program, I have given a lecture about what is real analysis. Only what is real analysis I have explained for 1 hour, or more than 1 hour. So real analysis is nothing but the calculus of real number system, or it is the development of real number system. Now today we are speaking about derivative, differentiation, and some applications of that. So actually, what is this differentiation? I hope there are in this gathering, there are some students I have seen in the participants. Students are there and some teachers are there. But whoever may be there in the audience group, differentiation. What is actually differentiation? Let us try to pronounce that word differentiation. Differentiation is nothing but you find a difference in that. So differentiation is nothing but it is the process of finding derivatives, finding the differences actually. It is the process of finding differences. See, if you see the fundamental principle of for the derivative, what do we understand from that? Suppose if we take two variables, basically x and y are two variables, where x is an independent variable and y is a dependent variable, and y is a function of x. We usually write y is equal to f of x or y is a function of x. Now, whenever y is a function of x, as x changes, y also changes. So as x changes independently, we call x as an independent variable. And as y changes, depending upon the value of x, y, we call it as a dependent variable. And we call y is equal to f of x as a function of x. Now, if we give some small increment in the value of x, say some small h. So if you give some small increment in the value of x, then x will be promoted to x plus h. So x moves to x plus h. Now, correspondingly, there will be change in the value of y. Initially at x, the function value y is f of x. And at x plus h, the function value is f of x plus h. Now, if you find the difference between these functional values, this is where differentiation comes into play. So if you find the difference between the functional values, that is f of x plus h minus f of x, corresponding to the change in the values of the independent variable, that is x plus h minus x. Now, if you find the comparison between them, the ratio between them, that is f of x plus h minus f of x by x plus h minus x. So numerator, if you observe, that is the difference between the function values. Denominator, if you observe, that is the difference in the independent variable values. So this ratio, finding this kind of systematic differences, ratio is for comparison only, as you know. So the difference between the functional values corresponding to the difference between the independent variable values. This process of measuring the differences in a systematic manner is called as differentiation. This is the process of differentiation. Now, the result after this process will be called as derivative. As we know what is addition, what is sum, what is multiplication, what is product, what is subtraction, what is difference, what is division, what is quotient, all these things you know. So these are all the addition, the multiplication, subtraction, division, these are all process. Operations are process. And whatever the result is there, that is sum. Sum is the result after addition. Difference is the result after subtraction. Product is the result after multiplication. Then quotient is the result after division. Right? Now, similarly, derivative is the result after the process of differentiation. Now, so, and also one more thing about real analysis is there. To understand real analysis, the best way is to understand the concept of limit. All the concepts that are there in real analysis, sequences is there, series is there, limits, continuity, differentiability, integrability, uniform continuity, whatever you speak in the higher stages at PG level, you will be studying Riemann-Stieltjes integrals, you will be studying metric spaces, you will be studying measure and integration, you will be studying function analysis and all that, whatever you study, wherever you go. And another one is complex analysis. So wherever you study about this kind of calculus, limit concept, continuity, differentiability, integrability, all these concepts can be understood by understanding only one concept, that is known as limit. So if you teach what is the concept of limit to the students perfectly, then it will be easy for them to understand the concepts of continuity, differentiability, integration, and every other concept. convergence, if you take sequences and series, convergence is also nothing but expressed in terms of limit. So dear teachers, teacher friends, and dear student friends, to understand real analysis, all the concepts of real analysis, in fact, any analysis, try to understand the concept of limit first. If you want me to explain about limit, only the concept of limit, it takes at least 1.5 hours. So that much criteria is there in limit. So anyway, we are going to use that concept in differentiability also. Just now we have studied about continuity. There we have already used the concept of limit. Now, with this introduction, let me enter into the topic. Now, these are the basic properties of the derivatives. And first of all, let us see a function f. Now, just now we have studied about continuity, and he was speaking about the function which is defined on a closed interval a comma b. And leaving the endpoints to my earlier speaker, I am only concentrating upon the open interval now. So because differentiability is there defined generally on open interval, whereas continuity is defined on closed interval. So let me take this real valued function which is defined on open interval a comma b. You know what is a real valued function? A real valued function is a function whose codomain is real number system. Here the domain for this function, when I'm saying f be a real valued function over open interval a comma b, this open interval a comma b will become the domain of this function f, and real valued function, the values, the images will become real numbers. So this function f is having real numbers as its images. The images of this function will be real number. This is a real valued function defined over a comma b. Now let C be any point inside this interval, that is C lies between a and b. C belongs to open interval a comma b. Now, as I told you, the concept of derivative differentiation depends upon the existence of limit. Now, if limit of this f of x minus f of c by x minus c, just now I was telling you about the fundamental principle, that is f of x plus h minus f of x plus h, f of x by x plus h minus x. That ratio, for that ratio, if you apply the limit, that is h tends to 0, I said that h is the small increment in the value of x. So if h is very small, whenever h is small value, with the small increment in the value of x, if you are able to find the difference between the functional values with respect to the difference between the independent variable values, then that value, if that value exists, then we say that that function is differentiable. Only to say that increment is very small, we use limit. So we are restricting the value h to be very small. That is the limit. That is the limit. So limit h tends to 0. Similarly, here also, the ratio f of x minus f of c by x minus c, this value exists and is finite as x tends to c. The value of x tends to c here. The value of x tends to c. X approaches to c. X tends to c. X is coming closer to c. X is in the neighborhood of c. So whenever x is approaching towards c, if the value of this f of x minus f of c by x minus c, if this exists, then we say that the limit exists, and also we say that the function f is differentiable at the point x is equal to c. There are different ways of expressing this. Unfortunately, I am taking this class from home as instructed by your head. So I don't have the facility of board here. So just I will be explaining with my hands. So limit x tends to c f of x minus f of c by x minus c. If this limit exists, then we say that f is differentiable at x is equal to c. Now, there are different ways of expressing this limit. X tends to c, if you see, that can be studied by using left-hand limit, right-hand limit concept also. Limit x tends to c, because this x tends to c can happen in two ways. One is because x tends to c, we are studying on the real line here. Whatever the concepts that we are studying in real analysis, they must be understood by keeping in view of real line in your mind. So c is on the real line, x is also on the real line, x is moving, c is a fixed point. Now the value of x is approaching towards c. When the value of x is approaching towards c, it may approach from the left side. That means the value of x may be less than c and approaching, coming closer to c. And the value of x may be greater than c and approaching towards c. The general example is, suppose you are in the second floor of an apartment or of a building. So the person who is there in the first floor, he is standing in a floor which is at a lesser height than you. So then he will be climbing the steps and he will be coming towards you. He will be approaching towards you by climbing the steps from the first floor to the second floor. That is one way. Now there may be a person who is there in the 5th floor and he will be approaching towards you by climbing down the steps, and he will be approaching towards you. So both the persons are approaching towards you. So similarly, x tends to c can happen in two ways. So the value of x may be less than c and x may be coming closer to c, approaching towards c. And the value of x may be greater than c and it may be gradually decreasing and approaching towards the value of c. So in both the cases, if this f of x minus f of c by x minus c exists, then we say that the function f is differentiable at x is equal to c. In the first case, when x is less than c and x tends to c, if limit x tends to c, if this limit value exists, f of x minus f of c by x minus c exists, then we say that it is left-hand derivative. In the second case, when x is greater than c and x tends to c, if f of x minus f of c by x minus c has a finite value, we say that it is the right-hand derivative. And if both these exist and are equal, we say that the function f is differentiable at x is equal to c. That is another way. Now, as I told you, when the function is differentiable, the outcome of this process will be the derivative. And that derivative is denoted by f dash of c. And f dash of c is equal to limit x tends to c f of x minus f of c by x minus c. Now, a function may be defined. Now, I told you that this function f is defined over this domain a comma b. But a function may be differentiable at some points of this domain, and it may not be differentiable in the entire domain here. Sometimes it may be differentiable in the entire domain also. So the domain of definition of f dash may be a subset of the domain of definition of the function f. That is what I have explained here. The function f is defined over a domain D, then f may or may not be differentiable at every point of the domain D. Now, we say that the function f is differentiable on the domain. For example, in this open interval a comma b, if it is differentiable at every point which is lying between a and b, it should be differentiable at every point of the domain, then only we say that the function f is differentiable. If at all this limit does not exist, in that case, we say that the function f is not differentiable at x is equal to c. Now, by using this definition, let us see some examples first. Now, the first example is like this. Using the definition of the derivative, using the definition of differentiation, find the derivative of this function f of x is equal to x square cos x at the point x is equal to 0. Now, one point I wish to say here is, if you are given with any polynomial like this, polynomial functions, trigonometric functions, exponential functions, logarithmic functions, these functions are generally continuous and differentiable in their definition of in their domain of definition. The function cos x will be having its own domain of definition, sin x will be having its own domain of definition. Similarly, e power x, log x, these functions are having their domains of definition, and in their domain of definition, these functions, the polynomial functions, constant functions, exponential functions, logarithmic functions, and these functions are always trigonometric functions, inverse trigonometric functions, hyperbolic functions. These functions are generally continuous functions and also differentiable functions. Now, at a particular point, we have to test by using this definition. Now, x square cos x, x square is polynomial, cos x is trigonometric function. Of course, cos x is also a polynomial. Now, f of x is equal to x square cos x, and the point given is c is equal to 0. Now, if you find the functional value, that is f of c, at c is equal to 0, you'll get f of 0, that is nothing but 0. As x is 0, this will become 0. Now, from the definition of derivative, if you see f dash c is nothing but limit x tends to c f of x minus f of c by x minus c. Actually, we are habituated to read this as limit x tends to c f of x minus f of c by x minus c. We should not read like this actually. We should read it as f of x minus f of c by x minus c as x tends to c. We should not read that limit x tends to c f of x minus f of c by x minus c, but from the childhood itself, we are habituated to read like this. But actually, we should read it as f dash c is equal to f of x minus f of c by x minus c as x tends to c. That is the way. Now, this is equal to, if you substitute these values f of x and f of c, this is x square cos x minus f of c is 0 by x minus 0, c is 0 here. And if you cancel and simplify, this is x cos x, and x cos x as x tends to 0, as x is 0 here, this will become cos 0 is 1 and this is 0, so the product will become 0. So this result will be known as f dash of c. So we are able to find f dash c. F dash c exists here, so the function is differentiable and the value of the derivative is 0. Now the second one, second concept is just now the earlier speaker, Dr. Rajkumar, has given about a thorough idea about continuity by showing so many graphs and all that. Now let us have a discussion between differentiability and continuity. So continuity is known to you. Now differentiability is also known to you. Now there is a relation between differentiability and continuity. Let us see that in the form of a theorem. If a function f is differentiable at a point x is equal to c, then the function f is continuous at x is equal to c. So every differentiable function is always continuous, and let us think of the converse of this theorem also. So this is over the years, this question has been very important in keeping you off examination, but in general also, it gives us a relation between differentiability and continuity, two different concepts of this real analysis. So now I will start with f is differentiable at the point x is equal to c. Just now we have seen that when the function is differentiable at x is equal to c, then the derivative exists, that is f dash c exists, and its value is given by f dash c is equal to limit x tends to c, f of x minus f of c by x minus c. So this is existing as it is differentiable. Now our claim is to show that that function is continuous at x is equal to c. So to test the continuity of this function, let us consider the difference between the functional values, that is f of x minus f of c. Now this is multiplying with x minus c and dividing with x minus c. This expression can be written as f of x minus f of c by x minus c into x minus c. Now this point is our interesting thing, that is if you apply limit on both sides now, limit x tends to c f of x minus f of c becomes limit x tends to c of this f of x minus f of c by x minus c into x minus c. Now this is nothing but limit of product, which is equal to product of the limits. So this is f of x minus f of c by x minus c. As x tends to c, its value is nothing but f dash c. And x minus c, as x tends to c, x minus c, this difference becomes 0. So f dash c into 0, that becomes 0. And if you see the left hand side, limit of the difference of two functions will be the difference of limits of the two functions. This is nothing but the homomorphism property. Limit of sum of two functions, limit of difference of two functions, limit of product of two functions. These are all homogeneous nature, homomorphism nature, and linearity property nature. So limit of this is f of x minus limit of f of c. And limit of f of x, this f of x as x tends to c remains as same. And this is f of c is only a constant here, and limit of this f of c will become only f of c. So your limit of f of x is becoming f of c. So this function is continuous. The value of the limit and the functional value both are equal. We say that that function is continuous. So the function is becoming continuous at x is equal to c. So every differentiable function, we have taken that f is differentiable at x is equal to c, and we have proved that the function f is differentiable at x is equal to c, continuous at x is equal to c. That means differentiability implies continuity. Now we will see whether continuity implies differentiability or not. In general, the answer is no. So a continuous function need not be differentiable. There may be some continuous functions which are differentiable, but in general, a continuous function need not be differentiable, because we have one example. This example has also been covered just now. So I consider the same one, f of x is equal to mod x at x is equal to 0. I am considering the point to be x is equal to 0 at origin. You know the nature of this function, this beautiful function modulus of x, the absolute value function modulus of x. So it gives you plus or minus x. When x is greater than 0, it will give you x, and if x is less than 0, it will give you minus x. So it gives you plus or minus x values, and it is the maximum of both x and minus x. Now, if you take epsilon and delta definition again, if you take epsilon and delta, these are in entire analysis and in any branch of abstract mathematics, in fact, both epsilon and delta, whenever you take them, they are always very small, positive, arbitrary real numbers. Please remember this small sentence about these epsilon and deltas. These two are always small, positive, arbitrary real numbers. Arbitrary in the sense they are not fixed. That is the sense. Small in the sense they are very much negligible quantities, very, 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 very small quantities. They are used for comparison. So epsilon and delta are always positive quantities, arbitrary real numbers, small quantities. Now, whenever this, the definition of continuity as given earlier, for every epsilon greater than 0, there exists a delta greater than 0 such that modulus of f of x minus f of c is less than epsilon whenever modulus of x minus c is less than delta. That is the definition. So now I approach in the same manner. So when c is equal to 0 here, mod x minus 0 is less than delta. Whenever this mod x minus 0 is less than delta, this mod f of x minus f of 0 should also be less than some epsilon. Then only we say that the function f is continuous. So if I take this mod x less than delta, then I am choosing here delta to be epsilon. Then if I consider mod f of x minus f of c, that is mod f of x minus f of 0, which is nothing but modulus of x minus 0, which is mod x. So this mod x value is already chosen to be less than delta. And delta is of course equal to epsilon. This is the reason why I was telling epsilon and delta are very much arbitrary constants. You can select as you wish. So epsilon is equal to delta here. That means I'm able to find out mod f of x minus f of 0, its value is less than this epsilon for every mod x minus 0 less than delta. Whenever this happens, we say that the function f is continuous at x is equal to 0. Now we will test the differentiability of this function mod x at x is equal to 0. For that we consider limit x tends to 0 f of x minus f of 0 by x minus 0. This f of x is nothing but mod x here, and f of 0, that is nothing but mod 0 is always 0, by this is x minus 0. Now mod x, as I told you, it gives you plus or minus x, and this is plus or minus x by x. That means it is giving you two values, either plus 1 or minus 1. If you want in detail also, you can find out the left hand limit and right hand limit. If you find the left hand limit, then you will get minus 1 because this value will become minus x. If you find the right hand limit, then you will get plus 1 because this value will become plus x. So that way you are getting two values, plus 1 and minus 1. So the left hand limit and right hand limit are not equal. So this function, the limit does not exist, so it cannot be differentiable. Now the other way is because a limit of this plus or minus x by x, then you are getting two values here, plus or minus 1. Whenever the value of the limit exists, that value should be always unique. But you are getting two values here, so this limit does not exist. Whenever this limit does not exist, then we say that the function f is not differentiable at x is equal to 0. So this modulus of x is an example of a function which is continuous at x is equal to 0, but not differentiable at x is equal to 0. That shows that a continuous function need not be differentiable. So this is the very much fundamental relation between differentiability and continuity. Every differentiable function will become continuous, but every continuous function need not be differentiable. Now we see the algebra of differentiable functions. This is the common feature when we study about algebra of continuous functions, algebra of differentiable functions, algebra of integrable functions, algebra of convergent sequences. Everywhere it is, the concept is same. Once we understand the concept, then we apply the differentiable, we apply the algebra of those functions. So if you take two functions f and g, these two functions are differentiable at the point x is equal to some a. Then all these functions f plus g, f minus g, k into f, f into g, f by g under some conditions, all these functions are also differentiable. This is the algebra of all these functions. So this function f plus g is also differentiable, and its derivative is given by this formula. F plus g dash of a is equal to f dash of a plus g dash of a. And similarly, f minus g dash of a is equal to f dash of a minus g dash of a. And if k is any constant, then constant time this f dash of a is equal to k into constant times of the derivative. This is also nothing but homomorphism property, or this is nothing but linearity property. K into f whole dash of a is equal to k into f dash of a. Now the product function f into g is also differentiable at x is equal to a, and this is nothing but your UB rule in calculus. F into g dash of a is equal to f of a into g dash of a plus f dash of a into g of a. Similarly, the quotient f by g is also differentiable at x is equal to a, provided this g of a, this denominator should not be equal to 0. This is nothing but u by v principle. This g of a into derivative of f at a minus f of a into derivative of g at a by g of a whole square. So all these functions are also differentiable. I am leaving the proof here. Going for the next one, that is nothing but composite function, which is also the algebra of two functions. Now, derivative of a composite function, this we also call it as chain rule. Suppose if the function f is differentiable at a point a, and g is another function which is differentiable at the image of this point, that is f of a, then the composite function g circle f is also differentiable at the point x is equal to a. and the derivative is given, that is G circle F dash of A. G circle F dash of A is equal to G dash of F of A into F dash of A. That means first we will be looking at the derivative of this first function, that is F dash of A. Then we will be seeing this function, that is G dash of F of A. The proof is very simple actually. I will tell you briefly. The function f is defined on an interval, say for example I, which is containing this point A, and GB, another function which is defined on the interval J, on the open interval J, now containing the point f of A. F of A is nothing but the image of this function. So now J is nothing but the image of this interval under the function f, that is J is equal to f of I. Now G circle f, you know the definition of G circle f. G circle f of x is nothing but G of f of x for all x belongs to I. Now we take f to be differentiable at x is equal to a. Now when the function f is differentiable at x is equal to a, that is the given information, we know that this limit exists, that is f dash a exists. Now it is also given that the function g is differentiable at x is equal to f of a. G is differentiable at f of a. So we apply that one, G circle f of x. G circle f of x minus G circle f of a by x minus a is equal to G of f of x minus G of f of a by x minus a, which is nothing but G of f of x minus G of f of a by f of x minus f of a into f of x minus f of a by x minus a. This is your equation 1. Now as the function f is differentiable at x is equal to a, the function f is continuous, as you know this fact. Now that means limit of this f of x will be equal to f of a. That means f of x tends to f of a. Now, if I apply limit on both sides here for this equation 1, then that will be equal to limit of this entire function, that is the product, will be equal to limit of the product of these two functions. Now, when I apply limit extends to a here, whenever limit extends to a, this f of x tends to f of a. So for this function, I will apply the limit f of x tends to f of a. I am using the concept of continuity here, because f is given to be differentiable at x is equal to a, the function f is continuous at x is equal to a. So that means whenever x tends to a here, f of x tends to f of a. That means when I am applying limit x tends to a, I can apply limit f of x tends to f of a. This is what we can do. Now this second limit exists here. The first limit also exists because the function f is continuous at x is equal to a. So this limit exists, and that is nothing but f dash of a. Because the function f, g of x, g is differentiable at f of a, this limit also exists. So this is nothing but g dash of f of a. So g dash of f of a into f dash of a, that is nothing but, that means the right hand side is existing here. When right hand side is existing, so the left hand side limit also exists here. That means when left hand side limit exists, the function g circle f will be differentiable at x is equal to a, and the derivative is given by g circle f dash of a is equal to g dash of f of a into f dash of a. So this is the chain rule or composite function. Now we see some examples on these composite rule and all that. Now, I have taken these examples from your prescribed book, that is Ross. Now, f of x is equal to x squared sine 1 by x when x is not equal to 0. I'm taking the examples of some special functions, not taking simple algebraic functions. So this is x squared sine 1 by x when x is not equal to 0, and its value will become 0 when x is equal to 0. This is the function which is defined like this. Now, there are 3 points that are to be studied here. We should show that the function f is differentiable at each x where that value is not equal to 0. At every non-zero value, the function is differentiable, and we should calculate that f dash of a. And again, by using the definition, we should show that f is differentiable at 0, and we should find f dash of 0. So in these two cases, we are proving at 0 individually, and for every non-zero element, we are proving that the function is differentiable. And we should prove that the derivative f dash is not continuous at x is equal to 0. It is not, f is not continuous at x is equal to 0, but it is the function f dash which is not continuous at x is equal to 0. So these are the 3 points I should prove here. So for that, to prove this, the function f is differentiable, to show that this first point, f is differentiable at any x not equal to 0 or a not equal to 0, I am using the definition of this product rule and also chain rule. So for that, I am defining 3 functions here. This, to get this x squared sine 1 by x, we are having x square function, we are having 1 by x function, and we are having this sine x function. So I'm taking f1x is equal to x square here, and f2x is equal to sine x, and f3x is equal to 1 by x for all x not equal to 0. And all these 3 functions are having different domains of definition, and all these functions are continuous functions and they are also differentiable functions. As I told you, these functions, polynomials and also trigonometric functions are continuous and differentiable. Now f1, f2, f3, all these functions are differentiable in their domains. Don't worry about this 1 by x also, because we are speaking when x is not equal to 0, this derivative exists. Only when x is equal to 0, it has a problem. Now, when these three functions are differentiable, just now we have seen that when f and g are differentiable, f circle g is also differentiable. Now, because f2 and f3 both are differentiable here, f2 circle f3 is also differentiable. Now I use f2 circle f3 of x here, that is nothing but f2 of f3 of x, which is nothing but f2 of f3 of x is nothing but 1 by x. So this is f2 of 1 by x. Now your f2 is nothing but sine x, so f2 of 1 by x will become sine 1 by x. So this function is also differentiable because of this chain rule. F2 circle f3 is also differentiable. Now, because f2 circle f3 is differentiable and f1 is also differentiable, whenever f and g are differentiable, f into g is also differentiable. Now f1 is differentiable, f2 f3 is also, f2 circle f3 is also differentiable. Then by product rule, f1 into f2 circle f3 is also differentiable. But f1 into f2 circle f3, f1 is nothing but x square and f2 circle f3 is nothing but sine 1 by x. So we get x square sine 1 by x, which is also differentiable for every non-zero value. So this x square sine 1 by x is nothing but our f of x. So this function is differentiable for every non-zero value of x. That is the first point. Now, second point is to show that f is differentiable at x is equal to 0. So for that, of course, f dash x also we can find. When the function is differentiable, you have seen UV rule in the earlier slides. You have seen UV rule. The rule you can apply here, x square sine 1 by x. X square into derivative of sine 1 by x, that is cos 1 by x, into derivative of this 1 by x, that is nothing but minus 1 by x square, plus again sine 1 by x is kept as it is and derivative of x square will become 2x. And you can get 2x sine 1 by x here, and these two terms will go and you will get minus cos 1 by x. Now at the point x is equal to a, you got this derivative 2a sine 1 by a minus cos 1 by a. Now, the second case is we should prove that the function is differentiable at x is equal to 0. That means let us consider f of x is equal to x square sine 1 by x. Now, at x is equal to 0, f of 0 will become 0. Now, from the, it is given to be 0. Now, from the definition of the derivative, f dash of x is equal to f of x minus f of a by x minus a as x tends to a. Now let us substitute f of x is equal to x square sine 1 by x, f of 0 is 0 and the denominator becomes x. So this is x square sine 1 by x, that will become x sine 1 by x. And if you bring this x to the denominator, then it will become sine 1 by x by 1 by x. Now here x tends to 0 is there. Whenever x tends to 0, then 1 by x tends to infinity here. Now 1 by x tends to infinity, then sine 1 by x by 1 by x. This is sine 1 by x by 1 by x now. As x tends to 0, 1 by x tends to infinity here. And for sine function, we have two formulae. One is sine theta by theta as theta tends to 0 will become 1. The other is sine theta by theta as theta tends to infinity will become 0. We use the second one here, so its value will become 0. So f dash of 0 is equal to 0. So the function is differentiable at x is equal to 0 also, and its derivative is also 0. Now the third point is, what is the third point? Show that f dash is not continuous at x is equal to 0. So we already know the value of f dash of x. So we are taking that f dash of x as 2x sine 1 by x minus cos 1 by x. Now, if you consider these functions, there is no problem with 2x, but there is a problem with sine 1 by x and cos 1 by x. These two functions cannot be defined at the point x is equal to 0. When the function is not at all defined at all, then the limit does not exist and the functional value does not exist. So the function is not continuous. For a function to be continuous, the function must be defined in the given interval. The functional value must be there at the desired point. And the limit of that function must be equal to the functional value. These are the three basic conditions for a function to be continuous. Now the function is not defined at the point x is equal to 0. So this function never will become continuous at the point x is equal to 0. So these are the 3 points that are proved. Now again use the another problem is again use the chain rule to show that this function sine of x cube plus 7x for all x belongs to R is differentiable everywhere and find its derivative. Again, I use chain rule here. To use chain rule, you can see that there is one function x cube or 7x here, and another function is sin x here. So I'm defining two functions, f of x is equal to x cube plus 7x, and g of x is nothing but sin x. Now, in this case, if I define like this, then if I consider g circle f of x, then that is g of f of x. G of f of x means nothing but x cube plus 7x. Now, g is nothing but sin x, so sin of x cube plus 7x. So this will be sin of x cube plus 7x, and this is our given function, which is nothing but h of x. So if I take f of x as x cube plus 7x and g of x as sin x, then my h of x will become g circle f of x. So that is my required function. That means I have converted this function h of x as a composite of two functions, that is g circle f of x. Now, if I show that this g circle f of x, g circle f is differentiable, then naturally your h will become differentiable. Now, what are f and g here? F and g both are polynomials here. You know, sin x is a polynomial having the expansion, Maclaurin series expansion of the form x minus x cubed by 3 plus x power 5 by 5 minus x power 7 by 7 and so on and so forth. So sin x is differentiable and it is continuous. X cubed plus 7x is a polynomial which is differentiable always. So both these functions are differentiable. So your g circle f is also differentiable. That means your h is also differentiable. And when this composite function is differentiable, then the derivative is given by the formula g circle f dash of x is g dash of f of x into f dash of x. Now, you know what is f dash of x. F of x is x cube plus 7x. Now, f dash x will become x cube. Derivative of x cube is 3x squared. Derivative of 7x is 7. And similarly, derivative of sin x will become cos x here. So if you substitute these two values, then you will get the result, that is cos of x cube plus 7 into 3x squared plus 7. That is the derivative of this h of x. Now, another formula we take, another example we take, cos x plus e power x whole power 12. So again, it is the combination of two functions, cos x plus e power x, and another one is the power function exponential, the exponent power function, that is x power 12. So I take cos x plus e power x as f of x, and I take x power 12 as g of x. If I consider the composite function g circle f of x, then I will get g of f of x, which is nothing but cos x plus e power x, g of f cos x plus e power x. Now g of x is x power 12. So g of cos x plus e power x will become cos x plus e power x power 12. Now, which is nothing but your given function, which we have taken it as h of x. So your h of x becomes g circle f of x. That is, your h is written as a composite function of these two functions. Now, as e power x is their exponential function, which is always differentiable. Cos x is a polynomial, which is always differentiable. X power 12 is also a polynomial, so this is always differentiable. So these functions are polynomials, hence they are differentiable. And then their composite function g circle f is also differentiable. And the derivative f dash x is given by derivative of e power x is e power x, derivative of cos x is minus sin x, derivative of x power 12 is 12x power 11. Now, by applying chain rule here, derivative of g circle f of x is nothing but g circle f dash of x, which is g dash of f of x into f dash of x. Now, if you substitute these f dash x and g dash x here, then you will be getting this result. This is the derivative of h dash of x. Now, another example is like this, x sine 1 by x, the previous one, for all x not equal to 0, and this is 0 when x is equal to 0. Now, we should show that this function is continuous, and this function, is it differentiable or not? That is what we will check. Now, this gives another example of a continuous function, and which may or may not be differentiable. Now, let us take this function f of x as x equal to 0. At x is equal to 0, it becomes 0. At x not equal to 0, it is x sine 1 by x. Let us again choose two small positive arbitrary real numbers, epsilon and delta. Let us choose that x minus c, mod x minus c is less than delta. That means c is 0 here. So mod x minus 0 is less than delta. Now I consider the difference between the functional values, that is modulus of f of x minus f of 0, which is nothing but modulus of x sine 1 by x minus 0, which is modulus of x sine 1 by x. Now modulus of product of two functions is equal to product of modulus of the two functions. So this is mod x into mod sine 1 by x. And from the properties of modulus of trigonometric functions, modulus of sin x is always less than or equal to 1. So this quantity can be substituted here. Thereby your mod f of x minus f of 0 will be less than or equal to mod x. And mod x is chosen to be less than delta. And by choosing this delta to be epsilon, we get that modulus of f of x minus f of 0 is less than epsilon whenever mod x minus 0 is less than delta. Now the function f is continuous at x is equal to 0. Now this shows that the continuity of the function. Now we will check about the differentiability of this. Now to test the differentiability, let us consider f of x minus f of 0 by x minus 0. Your f of x is x sine 1 by x, f of 0 is given to be 0 and by x minus 0. Now this x goes and you will get sine 1 by x. And you know that the limit of this function does not exist as x tends to 0. So this is where, again, I'm telling you, if you see these things, the first word I told you about understanding the concept of limit. If you understand the concept of limit, you can understand the concept of continuity and differentiability, integrability, everything. So if this limit does not exist, so we are speaking about the differentiability in terms of the limit here. So the function is not differentiable at x is equal to 0. So this is another example. X sine 1 by x is another example of a function which is continuous at origin but not differentiable. I hope these examples are enough. Better we move. Anyway, I'm leaving this here. We will see another another example, and then we will go to the next topic. F of x is equal to x square when x is rational. Such kind of problems are usually important in continuity, in differentiability, and in Riemann integration. Functions are defined when x is rational, when x is irrational, because your entire real number can be treated as the union of rationals and irrationals. The nature of the function may differ when the value of x is rational number, when the value of x is an irrational number. So when the function is behaving differently, when it is rational and when it is irrational, then how to study the continuity, how to study the differentiability, how to study the integrability of that function over a given interval. That is the important concept in real analysis on the real line. So in this discussion, we will take one such example. That is, a function value is x square when it is rational, and it becomes 0 when x is irrational. So we should show that this function is continuous at origin, and we should also show that it is differentiable, and we should find the derivative. So for that, the first case is to show that the function is continuous at x is equal to 0. Now I have to divide the proof of this into two parts. One is when x is rational, the other is when x is irrational. When x is rational number, it is given that f of x is equal to x square. Now, in the problem, actually, x is irrational. When x is irrational, f of x is given to be 0. The value of f of x is becoming 0 when x is irrational. The value of f of x is becoming x square when x is rational. Now we are discussing the continuity at x is equal to 0. So we should know what about this function value at 0 here. Now we know that 0 is a rational number. We know that 0 is a rational number because 0 can be written as 0 by 1, 0 by 2, 0 by p. Like that p by q form we can write it is purely a rational number. When it is a rational number, as per the definition, f of 0 will become 0 square, which is nothing but 0. So f of 0 is 0 and f of x is x square. So first we will check the continuity. For that we choose two arbitrary constants, epsilon and delta. Now let us take mod x minus 0 is less than delta, that is mod x is less than delta. Now consider the difference between these two, f of x minus f of 0, which is x square minus 0, which is mod x square. Because mod x is less than delta here, mod x square will be less than delta square. Now choosing this delta square to be epsilon, actually choosing delta to be root epsilon, we will be getting delta square is less than epsilon. That means the difference between f of x and f of 0 is less than epsilon whenever the difference between x and 0 is less than delta. Whenever this happens, that means whenever x is approaching towards 0, f of x is approaching towards f of 0. Whenever that happens, this function is continuous. You can see here, mod x minus 0 is less than delta. Why we speak continuity in modulus form? That is what one should understand. Modulus of f of x minus f of 0 is less than epsilon. Modulus will also give the distance between those 2 points. Modulus of f of x minus f of 0 is less than epsilon means the distance between f of x and f of 0 is less than epsilon. What is epsilon? Epsilon is a very small, minute quantity. Now the distance between f of x and f of 0 is less than epsilon means the distance between f of x and f of 0 is very, 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 very small. When the difference between f of x and f of 0 is very, very, very small means they are nearer to one another. They are very much close to one another. That means the value of f of x is very much near to f of 0. The value of f of x is nearing to f of 0. This is happening when mod x minus 0 is less than delta. That means whenever the value of x is very near to 0, the value of f of x is very near to f of 0. This is what the nature of continuity. So the function is continuous at x is equal to 0. Now, so this proves the first point, f is continuous at x is equal to 0 in the case when x is a rational number. Now we speak about x is a irrational number. When x is irrational, it is given that f of x is equal to 0. So clearly this function will become automatically continuous, because when x is irrational, the function value is becoming 0. And whatever may be the irrational number that you take, whether you take root 2, root 3, root 5, whatever, the function value is becoming 0. That means it is becoming a constant function. When it is a constant function, definitely it is always continuous. On the graph also you can see just now, our Rajkumar sir has shown the graphs for continuous functions. If you take a constant function, the ordinate, if you see, that becomes always a continuous function. Now f of x is equal to 0. Now f of 0 is as I told you, f of 0 is always 0. Now if you apply this f of x minus f of 0, then also it will become 0 minus 0, which is 0, absolutely less than delta. So it is choosing delta to be epsilon, it is less than epsilon. So again, it is satisfying this particular condition. So the function f is continuous at x is equal to 0. So in both the cases, whether x is rational or whether x is irrational, the function f is becoming continuous at x is equal to 0. Now the third point is to discuss about differentiability. So the function is, again, this is to be studied in both the cases, when x is rational and when x is irrational. When x is rational, f of x is x square, and as 0 is also a rational number, f of 0 is equal to 0. Now we consider this fraction f of x minus f of 0 by x minus 0, which is nothing but x square minus 0 by x minus 0, which is nothing but x square by x, which is nothing but x. So as x tends to 0, this will become 0. That means this limit is existing as x tends to 0. Therefore, the function is differentiable at x is equal to 0. That is, f dash 0 exists and its value is 0. So this is the case when x is rational. When x is irrational, f of x is given to be 0 and f of 0 is already 0. Now if you apply this limit x tends to 0, again f of x minus f of 0 by x minus 0, here both are 0, so numerator is 0, so it will become 0. So the limit exists, so the function is differentiable at x, so f dash 0 exists, and the function is differentiable at x is equal to 0, its value is 0. So the function is differentiable whether x is rational or whether x is irrational. So the function will be differentiable at every real number, and in particular at the value 0, its value will become 0. The derivative value will become 0. Now we have studied enough examples, I feel. Now I will move on to the next topic, that is mean value theorems. Now the first mean value theorem is this one. We always concentrate upon two mean value theorems and then the extension of them, Rolls and Lagrange's, but this is another wonderful mean value theorem that is like this. F is, again, read the words properly, please. Mean value, the value at a mean number, the derivative at a mean value, at a point which lies in the given interval. At an intermediate value, mean is nothing but intermediate one. Arithmetic, you know arithmetic mean, you know geometric mean, you know harmonic mean. If you take any two numbers a and b, if you take any two real numbers a and b, the arithmetic mean is nothing but a plus b by 2, which lies exactly in the middle of a and b. The geometric mean is root ab, which again lies between a and b. The harmonic mean is nothing but 2ab by a plus b, which again lies between a and b. So all these are the values which are lying between these two numbers a and b, and they are called as means. So arithmetic mean, geometric mean, and harmonic mean. Now these theorems that we are now going to study are also called as mean value theorems because of the same reason. So we are going to discuss about mean value theorem. We are going to discuss about the derivative of the function at a point which is mean, which is lying between the two endpoints that are given in the domain of definition. That's why, because the value of the derivative is discussed at a point which is lying at a in between the endpoints. That's why these theorems are known as mean value theorems. That is how we can understand the title. Now the first one is f is defined on an open interval containing the point x0, and f assumes its maximum and minimum at x0, maximum or minimum at x0. Then if f is differentiable at x0, then the derivative will become 0 at that point x0. The thing that we have to understand is vanishing of this derivative f dash of x naught will become 0 once if the function is differentiable, and at that point if this function assumes maximum or minimum. If the function has maximum value or minimum value at that point, and if the function is differentiable at that point, then we say the derivative will become 0. At a later stage, to find the maxima and minima and to find the extreme values, this is going to be a basic condition, necessary condition. So that is the one of the applications of the derivative. Now, if time permits, I will quote some of the applications of derivative at a later stage, if at all time permits and the organizers allow me. Now, f dash. Hello. Hello. Am I audible, please?
Yes, sir.
Yes, sir, you are audible. Yes, sir, you are audible.
Yes, sir.
My sites are visible and my audio is audible, right?
Yes, sir.
Shall I continue?
Yes, you are audible, sir.
Okay, thank you, thank you. So let the
Please
function
continue, sir. Right.
let f be defined on the open interval a comma b, and this open interval consisting of the point x naught here. That means x naught belongs to open interval a comma b. X naught lies between a and b. Now it is given that the function has either maxima or minima at x naught. I'm choosing that the function has a maxima at x naught. We can also prove the theorem by taking that f has a minima at x naught. Now, it is also given that the function is differentiable at x naught. In proving a theorem in analysis, in algebra, and wherever you prove theorems, always try to use the hypothesis to the maximum extent. A person who is not using the hypothesis to the maximum extent in proving the theorems is either a scientist or a fool. So I'm not either of them, so I will be using both. So f is differentiable at x naught, so that means f dash of x naught is equal to this, f of x minus f of x naught by x minus x naught. So as limit as x tends to x naught here. This is the derivative. This is the definition of the derivative. Now the thing is, we have to show that the value of this derivative is 0. So to show that the value of the derivative is 0, we will always assume that the derivative is not 0. At a later stage, because of this this supposition, we will be arriving at a contradiction, a result which is opposite to our known results. That is the situation where we speak about contradiction, and this contradiction arises only because of our some false suppositions. So then we will realize our mistake, and then we will come to the actual conclusion. So we suppose that f dash of x naught is not equal to 0. When it is not equal to 0, by the law of trichotomy, either it is greater than 0 or less than 0. So I am taking that f dash of x naught is greater than 0. When it is greater than 0, then in a small neighborhood of this x naught, that is x naught minus delta to x naught plus delta, actually we are taking modulus of x minus x naught is less than delta. That modulus of x minus x naught is less than delta indicates that the value of x always lies between x naught minus delta to x naught plus delta. So that is nothing but the neighborhood of the point x naught. So this is x naught minus delta to x naught plus delta, and this point is lying in this interval a comma b. This neighborhood is also there in a comma b. Now this neighborhood also belongs to a comma b because there is a signs here. The point x naught is lying between a and b. X naught belongs to the open interval a comma b here. Whenever x naught belongs to open interval a comma b, the neighborhood of x naught also lies in the interval a comma b. The reason is that this open interval is an open set. Every open interval is an open set. So every point of this open interval is an interior point of this open interval. So whenever a point belongs to this open interval, then the neighborhood of that point also entirely lies in this open interval. So when I choose this point x naught in this neighborhood, x naught in this interval a comma b, then the neighborhood of this x naught also is contained. A small neighborhood of this x naught is also contained in this open interval a comma b. That's the reason why we have taken x naught minus delta comma x naught plus delta also is contained in a comma b. Now, as f dash of x naught is greater than 0, f dash of x naught is nothing but f of x minus f of x naught by x minus x naught. This value is greater than 0 in this neighborhood. Now this is f of x minus f of x naught by x minus x naught is greater than 0. Thus that neighborhood is written in detail here. The value of x lies between x minus delta and x naught plus delta, but these are all the things lying between a and b, that is shown here. Now, when x belongs to this interval x minus delta comma x naught plus delta, then the value of x will be lying between x naught minus delta and x naught plus delta. Now, that means here as I told you, left hand limit, when the value of x lies between x naught minus delta to x naught plus delta, there may be a case that the value of x lies between to the left side of x, that is x naught minus delta to x naught, or x naught to x naught plus delta. So this interval x naught minus delta to x naught plus delta can be divided into two equal parts. One is x naught minus delta to x naught, that is bisection, and x naught to x naught plus delta. One is the right side of x naught, the other is to the left side of x naught. So if I take the right side part, that is x naught comma x naught plus delta, then the value of x lies between x naught and x naught plus delta. Now, this indicates that the value of x naught is less than x. That means x minus x is greater than x naught, so x minus x naught is positive. Now, if you apply in this, f of x minus f of x naught by x minus x naught is positive, so the denominator is positive here. Now, the fraction is positive. The fraction will be positive in two cases: when both the numerator and denominator are positive, or both the numerator and denominator are negative. Now, the fraction is positive, denominator is positive, so the numerator must be positive. That means f of x minus f of x naught should be positive. That is, f of x is greater than f of x naught for every value of x lying in this neighborhood of x naught. But we have assumed that the function f has a maximum at x naught. When the function has a maximum at x naught, the f of x naught value should be always more than all the values of f of x. But we got that f of x is greater than f of x naught. F of x naught should be greater than f of x actually, but we got f of x is greater than f of x naught. That means f cannot have a maximum at x naught. So this leads to a contradiction, and this contradiction arises because we have supposed that f dash of x naught is greater than 0. That means f dash of x naught is not greater than 0. Ikkada not greater than undalandi, పొరపాటు పడింది, అలానే కింది దాంట్లో కూడా. I'm sorry for that. F dash of x naught should not be greater than 0. Similarly, we can prove that f dash of x naught is not less than 0. So that indicates that f dash of x naught is equal to 0. So when you take that function, so we have proved that f dash of x naught is equal to 0 by taking that the function f has a maximum at x naught. So similarly, in the next case, that is when f has a minimum at x naught also, we can show that f dash of x naught is equal to 0. Now we prove an important theorem, that is Rolle's theorem. Now we are giving a different proof by using the previous mean value theorem for this Rolle's theorem, which is a very important theorem actually. Now a function f is defined on closed interval a comma b. Now I'm moving to closed interval because I need to define continuity also here. Now a function f is defined on closed interval a comma b, satisfying three conditions. F is continuous on closed interval a comma b, f is differentiable on open interval a comma b, and the value of the function is equal at the end point, that is f of a is equal to f of b. If these three conditions are satisfied by a function f, then there exists a point x or c between a and b at which the derivative will vanish, that is f dash of x is equal to 0. Now after the small proof, let us see the geometrical interpretation of this and the applications of this. Basically now I'm taking these three conditions: f is continuous on closed interval, differentiable on open interval, and the function value is same at the end points. Now my aim is to show that there exists a point between a and b at which the derivative is 0. So it is given that the function is continuous on closed interval a comma b. Now remember and just recall, we have seen some applications of continuous functions in the earlier class. So whenever the function f is continuous on closed interval a comma b, the function f will be bounded. The first application of continuity is it is bounded. Now it attains its bounds. It attains its supremum, its infimum, that is maximum and minimum on closed interval a comma b. And f takes every value between f of a and f of b. F takes every value which lies between infimum and supremum. These are all intermediate. If any point is lying between f of a and f of b, then just now intermediate value theorem is also studied. So there are so many opposite signs theorem, location of roots theorem is there, algebra of continuous functions is there. All those things are there, which is just now studied. Now I'm making use of that concept. If a function is continuous on closed interval a comma b, it is definitely bounded, and it attains its infimum and supremum, which we call them as maximum and minimum. So the function is having maxima and minima on closed interval a comma b. So I'm taking that the maxima exists, maxima and minima exist at these points x naught comma y naught. Attains here. Attains means it takes, it receives, it accepts the maxima and minima at any 2 points of this interval. So I'm taking 2 points, x0 comma y0 belongs to closed interval a comma b, and at x0 we have the minimum, and at y0 we have the maximum. That means f of x0 will become minimum, f of y0 will become maximum for the function f on closed interval a comma b. Then all the values of this function f will be lying between f of x0 and f of y0. So f of x0 less than or equal to f of x less than or equal to f of y0, and this is true for every value of x belongs to this interval a comma b. This is my expression 1. Now, if x0 and y0 are the endpoints, or the endpoints of this closed interval a comma b, and because of this, because x0 and y0 are lying between a and b, they may become endpoints also, they may not become endpoints. So if they are endpoints, then what happens? If they are not endpoints, then what happens? So if they are endpoints, as from the third condition, the value of the function is equal at the endpoints. So f of a and f of b are equal. That means f of x0 and f of y0 are equal in this case. F of x0 and f of y0 are equal means the maximum and minimum are becoming equal. When the maximum and minimum are becoming equal, that function will become constant function. When it is a constant function, the derivative definitely vanishes. So f dash of x will be equal to 0 for all x, not for a particular point x, but the derivative of this function will become 0 at every point of x in the case when they are endpoints. If they are not endpoints, then they will lie between the endpoint, that is a and b. That means they lie in the open interval a comma b. Now, then the function this function f is having a maximum at a point in between a and b now, because x0 and y0 are not the endpoints here. Now, the function now, according to second condition, the function, because the function is continuous, so it will be having minimum or maximum at this point. Now, according to previous theorem, if a function has minimum or maximum at any point, say x0 between a and b, and if that function is differentiable, because f is given to be differentiable here, then we know that the derivative is 0 at that point. So the derivative will become 0. Just now we have proved that theorem. I will show you again. This is the thing that we have seen. If f has maxima or minima and f is differentiable at that point, then the derivative will become 0. This is the theorem. Now the same theorem, if you apply here, then you will get f dash x is equal to 0. So there will be definitely a point where the derivative vanishes. This is what the thing is. Now if you see the interpretation here, suppose if you consider any curve y is equal to f of x as shown in this figure. Now this is the usual xy plane, and this is the point a comma 0, which is lying, this is the x coordinate, this is a comma 0, and this is b comma 0. Now a curve is drawn here. This curve represents your y is equal to f of x, which is continuous in the interval a comma b, and this is what I have represented. This point is my f of a, and this point is my f of b. Now this point will be a comma f of a, and this is b comma f of b, and it is clearly mentioned that this a comma f of a and f of b both are equal here. The functional values are becoming equal here. Now if you take any point, if you draw the curve like this, then if you draw the tangent to this curve, then the tangent to this curve will be touching at one point, say C, and this tangent will be parallel to the x-axis. When the tangent is parallel to this x-axis, then the derivative at this point will become 0. So that is what the geometrical interpretation of this. Y is equal to f of x be a continuous function on AB. Now it is clear that between the points A and B with equal ordinates, f of A is equal to f of B on the graph F, there exists at least one point, say C, where the tangent is parallel to x-axis. Now we see a couple of problems on Rolle's theorem. Now this is your f of x, x minus a whole power m and x minus b whole power n, where m and n both are positive integers. For all x belongs to a comma b, m and n should be positive, please. And for all x belongs to closed interval a comma b. Now clearly the function is x minus a whole power m into x minus b whole power n. Clearly this function is a polynomial, something like x minus 2 whole square, x minus 5 whole cube, like that. This is definitely a polynomial. Now every polynomial function is treated to be continuous always, and it is differentiable on the given interval. So function is continuous on closed interval and differentiable on open interval. First two conditions are satisfied. Now f of a, if you consider it x is equal to a, this will become a minus a, so it will become 0. at x is equal to b, f of b, that will become b minus b, so it will become 0. So your f of a is 0 and f of b is 0. So the functional value is becoming 0, and so the f of a and f of b both are becoming equal here. So these are the three conditions of Rolle's theorem. Then by Rolle's theorem, there exists a point C between a and b such that f dash of c is equal to 0. Now to find f dash c, let us differentiate this function f of x by using UV method. So if you differentiate like that, then you will be getting f dash of x, and f dash of x is equal to UV rule. If you apply m into x minus a power m minus 1 into x minus b power n, similarly plus n into x minus a power m into derivative of this x minus b power n minus 1. Now, because f dash c is equal to 0, if you substitute x is equal to c and equate this expression to 0, then you will be getting this m into c minus a power m minus 1, c minus b power n, and n into c minus a power m and c minus b power n minus 1. And we can take common the c minus a power m minus 1 and c minus b power n minus 1 can be taken common. And this is m into c, because this polynomial, this cannot be 0, so the second factor is 0. So on simplification, you will be getting c is equal to na plus mb by m plus n. Now if you see this one, this is the coordinates of a point which divides the line joining the 2 points a and b internally in the ratio m is to n. So this point c, n into a plus m into b by m plus n. So this point always lies between a and b, which divides the line joining the 2 points a and b in the ratio m is to n internally. So this point definitely lies inside that. So this is how we can find out. And at this point, the tangent will be parallel to the x-axis for the given curve. Now, if you see the next example, that is f of x is equal to 1 minus x minus 1 power 2 by 3 on closed interval 0, 2. Don't be under the impression that this is also a polynomial. To be polynomial, this x minus 1 power should be an integer always, should be a positive integer. So x minus 1 power 2 by 3 is there. It is not an integer, it is a fraction. So this we need not consider it as a polynomial. Now for such kind of things, how to test the conditions of Rolle's theorem or Lagrange's theorem or mean value theorem? For that, first we will go to differentiability. And we will check the derivative, that is f dash x. So we will check whether the function is differentiable or not. If the function is differentiable, now differentiability is tested on open interval. So when the function is differentiable on the open interval, then definitely on the open interval, the function will be continuous. But continuity is tested on the closed interval. So at the end points, we should test the continuity. Thereby, we can confirm the continuity on the closed interval. So first we will check whether the function is differentiable or not. So if you find the derivative of this function, derivative of 1 is 0 and derivative of this x minus 1 power 2 by 3 becomes 2 by 3 into x minus 1 power minus 1 by 3 with minus sign. But if you see this function, this is f dash of x. Now this f dash of x is minus 2 by 3 into x minus 1 power 1 by 3. Clearly, this function cannot be differentiable at x is equal to 1, and 1 is a point of this interval 0, 2. So the function is not differentiable at x is equal to 1. So function is not differentiable on 0, 2. So we need not now test any other condition. If at all this function is differentiable on open interval, then it will be differentiable on closed interval also, continuous on closed interval also. Then we have to test the continuity on at the end points. Then we have to confirm whether the function is continuous or not. Then we will go for the functional values f of 0 and f of 2. But this function is not differentiable at x is equal to 1. So we need not check any other condition. So this condition is the second condition of Rolle's theorem hypothesis is not satisfied. So we cannot apply this Rolle's theorem. Similarly, the another important example is this one. Prove that between any two real roots of e power x sin x is equal to 1, there is at least one real root of e power x plus e power x cos x plus 1 is equal to 0. So now I consider this function, actually it is not given that apply this particular mean value theorem or that theorem, but when we are speaking about roots, let us try to apply this Rolle's theorem. I will tell you one important point here after proving this result. Now the given function is e power x sin x is equal to 1. Now this can be written as sin x is equal to 1 by x, which is e power minus x. So I can rewrite this equation as sin x minus e power minus x is equal to 0. Now I take this sin x minus e power minus x as my f of x. Now here this is sin x is a trigonometric function which is always continuous and differentiable. E power minus x is an exponential function which is always continuous and differentiable on any given interval. So they are always continuous and differentiable. Now, now, if I take A and B, what is the hypothesis given here is between any two real roots of this. So I'm taking two real roots of this now, say A and B. So this is A and B are the roots of this equation. That means f of A is nothing but f of x is nothing but sin x minus e power minus x or e power minus x minus sin x. So this is e power minus a minus common this e power minus a minus sin a, that is 0. Because a is a root here, f of a will become 0. Similarly, this is f of b. Now, if I consider f dash of x, what is f dash of x here? F dash of x is nothing but minus e power minus x and derivative of sin x, that is of course cos x. Now, by Rolle's theorem, there is a point because f is already continuous and differentiable here, and f of a and f of b both are becoming equal and equal to 0 here. Thereby, by Rolle's theorem, we will be having a point C between A and B such that f dash C is equal to 0. So f dash C, if you substitute x is equal to C in this, you will get e power minus C plus cos C is equal to 0. That is nothing but e power C plus cos C plus 1 is equal to 0 after simplification. Now, this is the value where which is obtained by substituting x is equal to C in e power x plus cos x, e power x cos x plus 1 is equal to 0. So your e power x plus cos x plus 1 is equal to 0 is having a root at x is equal to C, where that C is nothing but lying between A and B. That means this C is a root of f dash of x. So f dash of x, there is at least one real root of this. E power x cos x plus 1 is equal to 0. So e power x cos x, this if you take minus out, this is nothing but e power x cos x is here. So one point that I am interested to say here is e power x sin x is equal to 1. This function is having two roots. Then the derivative is having a root at a point which is lying between A and B. So if you go back to that Rolle's theorem statement, so if at all this, if you impose another condition here, f of A is equal to f of B is already there. Actually in R.G. Bartlett book, the condition will be given like this: f of A is equal to f of B is equal to 0. That means these two values are, hello? F of A and f of B both are given to be equal to 0. That means A and B are becoming roots of this function f. In that case, f is continuous, f is differentiable, and f of A is equal to f of B is equal to 0. That means A and B are roots of this equation. Then there exists a point x between A and B such that f dash of x is equal to 0. That this A and B are roots of this equation. Now there is a value x such that f dash x is equal to 0. When f dash x is equal to 0 or f dash c is equal to 0, that c or x will become a root of this f dash of x. That means between the two roots of f of x, there is a root of f dash of x. If there is a, when you know two roots of a function, say a and b, then there exists a point c, which is the root of f dash of x, that is f dash of c is equal to 0. So to find out the root of the derivative of a function, you can always search between the two roots of that given function. That is the beauty of Rolle's theorem. This should be visualized always, please. Now this is what is Lagrange's theorem. Samashura garu, are you there?
Sir, tell me, sir.
Can I continue 10 more minutes? I should. I want to finish off this Lagrange's and Cauchy's mean value theorem with a couple of examples and speak about these some general points also. Shall I continue for 10 minutes? Anjani madam.
Yes, sir. Yes, sir. You can continue.
Okay, thank you. So this is Lagrange's mean value theorem. The function is continuous on closed interval a comma b, differentiable on open interval a comma b. Two conditions are there. The third condition of Rolle's theorem is not there here. Now there will be a point between a and b such that f dash of x will become f of b minus f of a by b minus a. Now, to prove this Lagrange's mean value theorem, let us define a function g, and we are proving this theorem as an application of Rolle's theorem. Now, let us define a function g on closed interval a comma b such that g of x is equal to this f of x plus k times x for all x belongs to closed interval a comma b, where this function f is given function and x is the variable here, and this k is a constant. Actually, this constant is to be chosen such that it satisfies, this function satisfies the third condition of Rolle's theorem, that is g of a is equal to g of b. Now, by defining a function like this, what is that we are going to elicit here? Now, because the right hand side f is continuous, given to be continuous on closed interval a comma b, x is always differentiable, hence is always continuous, and k is only a constant which is always continuous and differentiable. So the sum of these functions is always a continuous function. So your g will become continuous on closed interval a comma b. Similarly, g will become differentiable on open interval a comma b. Now we are choosing the constant k such that g of a is equal to g of b. When we are choosing the constant g of a is equal to g of b, then the three conditions of Rolle's theorem are naturally satisfied. So when g of a is equal to g of b, actually g of x is f of x plus k into x, g of a is f of a plus k into a, and g of b is f of b plus k into b. From this value of k is f of b minus f of a by a minus b. Now, as g of a is equal to g of b, g is differentiable on open interval a comma b, g is continuous on closed interval a comma b, the function g is satisfying all the three conditions of Rolle's theorem. So by Rolle's theorem, there exists a point x between a and b such that g dash of x is equal to 0. That means g dash of x is nothing but f dash of x plus k is g dash of x. G of x is known to you, f of x plus k into x. G dash of x will become, this is f dash x plus k into derivative of x is 1. So f dash x plus k, that is the derivative of g of x. So g dash of x is nothing but f dash x plus k is equal to 0. That means f dash x is equal to minus k. You know the value of k here. Substituting here, you will be getting f of b minus f of a by b minus a. And this is nothing but your f dash x. This is what we need to prove. Actually, we have proved this Lagrange's theorem by making use of Rolle's theorem. But if you observe this Lagrange's theorem, your Rolle's theorem will become a specific case of this Lagrange's theorem. Because if you apply the third condition in this, that is f of b is equal to f of a here in the numerator, then your f dash x will become 0. And that is what the result of Rolle's theorem. So if you apply that third condition of Rolle's theorem here, then you will be getting the result of Rolle's theorem. So this is generalized one. By applying the condition of Rolle's theorem, you will get that result of the Rolle's theorem here. Now, this is the geometrical interpretation where the tangent here will be parallel to the chord joining the points A and B. In the case of Rolle's theorem, the tangent will be parallel to the x-axis. In the case of Lagrange's theorem, because the functional values are not equal at the points A and B, we draw a chord joining A and B, and your tangent will be parallel to this chord joining A and B. This is the difference. Now, these are some applications of Lagrange's theorem and also Rolle's theorem. Just I will give the statements. I'll leave the proofs as time constraint. F is differentiable on the open interval, and if f dash x is equal to 0, then the function f will become constant function. In intermediate, we will be saying that if the derivative is 0, then it becomes constant function. So if the function is differentiable at that point and on that interval, and if the derivative is 0 for every point in that interval, then the function becomes a constant function. So this is the proof of that by using mean value theorem. And another corollary is if f and g both are differentiable on a comma b, whose values of the derivatives are equal, f dash of x and g dash of x both are equal for every point. That means having their derivative values are also equal, then the functions will differ by only a constant. That means f of x minus g of x will be equal to c, or you can write it as f of x is equal to g of x plus c. This is another application of the same Lagrange's mean value theorem. Now we have another applications by using the derivative. We can discuss about increasing and decreasing functions. This is the corollary. If f dash of x is greater than 0, then we say that the function f is increasing. This is one of the applications of differentiability. You can decide the increasing and decreasingness, monotonicness of the function, monotonically increasing functions, decreasing functions that can be decided by making use of the derivatives, strictly increasing, strictly decreasing, increasing and decreasing functions. That is also an application of mean value theorem and derivative. This is the corollary, and I have given proofs. And as in the case of continuity, there is an intermediate value theorem for continuous functions and intermediate value theorem for differentiable functions also. That means if the function f is differentiable on open interval a comma b, and if there is any point between, if you take any 2 points x1 and x2 between a and b, if the point c lies between the derivatives of these two functions, f dash of x1 and f dash of x2, and if the point c lies between these two, that means c is the intermediate value between the derivatives, then there exists a point x between these x1 and x2 such that f dash of x is equal to c. That means if the point c lies between the derivatives of 2 points, then this point c will also become derivative of some point here. The intermediate value will also become derivative of some point. So that is what the intermediate value theorem for derivatives. I'm skipping the proof again. And these are the examples on mean value theorems. That is Lagrange's mean value theorem. X square sin x, special functions I have taken here. Only first one is the basic algebraic function. This is trigonometric function. This is modulus function. This is signature function, which is very important one. This is reciprocal function. This is also reciprocal. I have changed the domain here, -1, 1. This is 1, 3. I have given the proofs in detail here. And this is another problem. By using Lagrange's mean value theorem, we can prove this result. Cos x minus cos y is less than or equal to mod x minus y. This is a really beautiful result by using Lagrange's mean value theorem. The distance between two functional values is less than or equal to mod x minus y. And sin x is always less than or equal to x for every non-negative value. And this is another mean value theorem, Cauchy's mean value theorem or generalized mean value theorem. This is applied for two functions. This is also similar to Lagrange's mean value theorem, but applied for two functions. F and G both are continuous on closed interval a comma b and differentiable on open interval a comma b. Then there is a point x lying between a and b such that f dash x by g dash x is equal to f of b minus f of a by g of b minus g of a. The proof is similar to the previous one. If you define a function h such that h of x is equal to f of x plus k into g of x, instead of x we take g of x here, and because f and g both are continuous, k is a constant, h is continuous here. As f and g are differentiable, k is a constant, h is also differentiable. So it satisfies both the conditions of Rolle's theorem, and here the constant k is to be determined such that it satisfies the third condition of Rolle's theorem, that is h of a is equal to h of b. If you apply this condition, you get the value of k, that is f of a minus f of b by g of b minus g of a. And if you apply Rolle's theorem now, then there will be a point between a and b whose derivative will become 0. Now, derivative of this function is nothing but h dash x is nothing but f dash x plus k into g dash of x, that is 0. So f dash x by g dash x is minus k. Again, if you substitute the value of this k here, then you will be getting f dash x by g dash x is equal to f of b minus f of a by g of b minus g of a. This is about Cauchy's mean value theorem. And these are a couple of problems on Cauchy's mean value theorem. Now, these are my references. And I want to show the lecture I have given about mean value theorems and differentiation. But for the benefit of students and for the benefit of younger teachers, I have two observations here. One is this one, JOM. I hope all the students may be knowing about this JOM. This is the examination, entrance examination that will be conducted by central universities for the admissions into PG courses for MSc Mathematics, just like Central University of Hyderabad and other central universities will be conducting this examination. Just like we have common entrance examination for state universities for MSc, and this will be the entrance examination for the MSc for the admission in central universities. So this is the site I'm giving the link. And if you link this one, you will be able to see some particulars about JAM. And I am also sharing the previous question papers and the paper pattern, and also for the benefit of the students. I request the teachers of this college and whoever is following this lecture through YouTube or this Zoom, please inform your students and ask your students to undergo this examination. And this is really useful for the students, please. So these are all the PDFs that I have mentioned here. This is shared from the Google Drive. So these are all the question papers. One of my research scholar has collected all these working as a lecturer. So from that research scholar, I have brought this. So please see this because time is very much limited here. I'm not going into the details. Please, you can click on any of these PDFs and you can just download that. These are test papers from 2010. You are having test papers here, model papers, the instructions and all that is there here, the question papers. All the teachers can see this, and the students who are interested can see. Teachers can make use of these things, and when you are teaching these questions, you can solve and show them to the students in your regular classes. So this is how the question paper, model paper is there and all that. So please see that I have also mentioned the paper details and all that. Several question papers are there. Please, please make use of that. Another point, if you permit me, another point is that about SWAYAM and online courses. Actually, I have been visited to your college to give a lecture on SWAYAM in the last year when you are going for NAC by your officer, nodal officer or in charge for this online courses. But due to hectic schedule that you are having, that I was having at that time, it was not possible for me to address about this SWAYAM courses. But when time permits or when you give me time, so I'm ready to give about this SWAYAM courses, which is very, very useful, particularly in this pandemic situation where all of us are making use of these online courses. This SWAYAM is useful for the students and for also for the faculty members. Only thing it demands is a Gmail account. If you have that Gmail account, then you can see all these courses. Just you can sign in here. Is my screen visible, please?
Yes, sir.
You just
Yes, sir.
right side you are having sign in or register. Just if you click, then you can enter into that sign in. If you have Gmail ID directly, you can enter. You can enter through Facebook also, but I don't recommend that Facebook. But if you have Gmail ID, then just enter into the. You can enter into that Gmail courses. All these SWAYAM courses. The present audience are enough for me. I don't require that infants are just children, very small children, please. So these are all the courses. You can, enrollment is open now. Ongoing courses are there. Enrollment is open. Now you can see all these courses. All these courses, they are sponsored by IGNOU. They are sponsored by NPTEL. And all these courses you can visualize, please. There are thousands of courses that you can see really. And you will appreciate there are so many courses here also. Course catalog, you can search like this. See mathematics, if you click here. I'm not only suggesting mathematics, any course. You can do music courses also. You can do literature courses. You can learn the computer science courses. These courses you can see. So this is about mathematics courses. computational mathematics, discrete mathematics is there. Now these are all from IIIT. This IIT, and this is engineering mathematics, financial mathematics, and these are all mathematics for school standard. This is secondary mathematics. So many courses are there. Undergraduate courses are there, postgraduate courses are there. You can also type here partial differential equations, measure theory, operational research, complex analysis, C language, which we have already searched. I have already searched, and I am doing 4 courses here. Similarly, teachers can do courses here and students can do courses. Various courses you can do by sitting just before your system. And you can write an examination conducted by NPTEL and SWAYAM courses. You can get the certificate, and that certificate has validity, and that you can show in your degree memo also. In memo, there is a validity for this, and teachers can also show in their CV, and in cash promotions also there is a validity. ARPIT courses are there, ARPIT courses are there. They are nothing but refresher courses. So the refresher courses are also useful for the faculty members in their cash promotions. I did one of this course earlier. Presently also I am doing one course. So I recommend these online refresher courses for the faculty members, and online courses for, see here, online refresher course for chemistry, ARPIT courses. This is our fifth course in commerce here. This is our fifth course in commerce again. In economics is there, in pharmacy is there. Last time we have mathematics course, and there are interdisciplinary courses, multidisciplinary courses are also there. You can learn English courses here. You can learn personality courses here. You can learn languages here. Yes.
Sir, your screen is not updated, sir. Only JAM details is coming.
Okay, okay, I will show you in another slide. Are you not able to see SWAYAM here?
No, sir. Only JAM details is
Sir,
coming.
your presentation is here.
Okay, okay, I will show about this. Haven't you seen SWAYAM now?
No, no, sir.
Okay, you have told me. Okay.
Sir, share once again, sir, please.
Okay, okay, okay. I will show you. I will show you.
Yeah, thank you.
I am stopping my this presentation and I am entering through another this one. Now, is my screen visible, please?
Yes, sir. Now
Yes,
it is
sir.
visible, sir.
Okay.
Yes,
Now,
sir. Visible, sir.
okay, okay. This is about SWAYAM. You have faculty development and student monitoring, mentorings. Both are there here for faculty and for students. This is about SWAYAM. If you click this, you will know what about SWAYAM and all the details will be there. This is about.
Oh, we can't see the details of SWAYAM, sir. Yours.
Madam, pardon?
No, no. We can see your screen, but there we can't see any details of SWAYAM, sir.
You just see now.
Open like.
If you see, you see now about SWAYAM, you know.
Okay, okay, okay.
Now you can see about the particulars of SWAYAM. You can read these details. You can click just in your Google bar, just you type SWAYAM, SWAYAM. If you just click, then you will be able to see the homepage of SWAYAM. And about SWAYAM, if you click all these details, you will get. And if you click this all courses here, just if you click this all courses, then all courses will be loading like this. Okay. Now, these are all the different courses now. Agricultural policy, libraries, ICT in libraries, cooperatives, and Indian agricultural development, project analysis. Plenty of courses are there. And you can also, if you want, this talent acquisition and management, technology forecasting, testing of functionals, testing textiles, variety of courses are there. Thermodynamics for physics students, for physics faculty, thermodynamics course is there. Thermodynamics for biology system is there, applications are there. You have operations research course is there, or operations research mathematics course is there. So one course I have opened for you. This is Introduction to Operation Research. So if you open that course, then you can see the details of that course. And you can also see the course layout here, how many units are there, what is the pattern of the course. And course is upcoming, 8 weeks course is there. This starts on 15th February and it ends on 9th April here. Exam date will be on 25th April. And enrollment, you can enroll now and the enrollment ends on 15th. And this is an AICT approved FDP course, faculty development course. And there is a huge validity for all the faculty members if you do such kind of courses. This is approved by AICTE and approved by FDP, approved by NPTEL and also SWAYAM. But you will only get this certificate once if you write this examination and submit the assignments. And this certificate will be very, very useful in your CV and also very useful in your CAS promotions. And this is also useful for all the students. So if you just click this one, he will be explaining about the course details and how to enter into the course. Now, if you see this join button, just if you press this join button, you will be enrolled into this. This is as simple as clicking a button. If you click this join button, then you will be joined into that course and you will be getting a message that you are enrolled to this course. And everything about this course will be sent to your mail. When is the first assignment? When is the second assignment? When you are able to see the videos. You can see these videos, preloaded videos at any of your free time in the entire day. So you can easily visualize this. This is only my introduction to SWAYAM courses, please. When you give me time, we can have a separate lecture on that. And also about JAM also, these are all the PDFs I have shared with you. With that link you can see, and you can do wonders by joining SWAYAM courses. And I request the students to write this examination, please, JAM examination. Right, coming back to your presentation kind of thing. Now, please interact with me now. Any questions, any abuses, anything, please try to interact with me.
Okay, thank you, sir.
Sorry,
Thank you for such an...
I have taken 15 more minutes.
Yes.
No problem, sir. No problem, sir.
It's okay, sir. It's okay.
Very informative and interesting also.
Thank you for such an informative session, sir. And first of all, I want to thank you for giving your WhatsApp numbers, phone numbers, and mail ID to clear the doubts of the participants. It's so generous, sir. You are so generous. Thank you very much for that. And you tried to make your presentation very simple and clear to reach the students among the participants. You observe that there are so many students in this webinar and try to make it very simple. Thank you very much for that. And you mentioned SWAYAM courses also. Even most of our faculty are doing SWAYAM courses. Personally, I have done 2 courses, and at present I am doing a course called Understanding Ethnography. I finished a Spanish proficiency course and a refresher course also. Thank you very much, sir, for being with us. And participants have the golden chance to contact the sir directly to clear your doubts. You can mail your doubts or you can call sir. Sir is available and he gave his numbers and mail ID. Thank you very much, sir.
Thank you. One word from my side. I thank all the principal and Anjani madam, my friends in the department, Samshirao Garu, very old friend of mine, Mr. Srinivas Garu, and another old friend, Saroja. I also thank Dr. Tirumala Devi for having suggested my name, and Dr. Saroja for suggested my name for this. And I thank Sambashira Garu, Srinivas Garu for approaching us. And in future also we are ready. I'm very much interested in teaching abstract papers. It is not that I don't teach other papers, but I'm very much interested in abstract papers. I will put my heart and mind into in such kind of papers. Thank you very much for the opportunity. You are ready to interact at any time, but after 4 o'clock would be better, because before 4 there will be no signals in the department. So after 4 you can call me, you can mail me anytime, you can WhatsApp me. I'm ready to interact with you. Thank you very much for the wonderful opportunity.
Thank you, sir.
Thank you, sir.
Thank you for your proposal.
Thank you, sir.
Thank you, sir.
Thank you very, very much, sir.
Thank you. Thank you.
Thank you, sir.
Okay, thank you.
Thank you so much, sir.
Okay.
Okay.
Please mute your audio, please. Please mute your audio, please.
Participants, you will get your feedback link in the chat box after vote of thanks.
Thank you, sir.
You can fill the forms to get your certificates. Every day 100 participants will get the certificates. We'll open this link for nearly a week. No need to worry. A recorded version of this webinar will be available. You can that link also in WhatsApp groups. So now I request our Assistant Professor of Mathematics, K. Srinivas Garu, to propose vote of thanks. So over to Srinivas, sir.
As all good things come to an end in life, so is a national webinar. Good afternoon to the honorable resource persons, respected principal, IQAC coordinator, dear participants, and my dear colleagues. It's my privilege to have been asked to propose a vote of thanks on this occasion of national webinar on concept of real analysis. I, K. Srinivas, on behalf of the Department of Mathematics, SRN Vizianar Government Degree College, Autonomous Khammam, Telangana State, and the entire organizers team, on my own behalf, extend a very hearty vote of thanks to our resource persons for gracing your important work and sharing with us. A special thanks to Dr. L.P. Rajkumar sir for his excellent efforts towards continuity of functions and uniform continued functions. We are really enlightened with your knowledge on this topic. Sir, you have given a lot of information about the topics. You have explained how continuous functions are applicable in real life and banks and other than mathematics subjects also. Once again, I would like to say my sincere thanks to you, sir, on behalf of our Department of Mathematics. At the same time, I would like to say my heartfelt thanks to another resource person, Dr. Bharvi Sharma sir, for his excellent lecture on differentiation and mean value theorems. Sir, you have given a lot of information about the topic, and also you have given a lot of information about JAM and SWAYAM. It is very useful to us, sir. Once again, I would like to say my heartfelt thanks to you, sir. Now it is the time to say my sincere thanks to our principal, Sri K.S.S. Ratnaprasad sir, who is the chairperson of the webinar, has encouraged and given permission to us to conduct this national webinar. I also wish to express my gratitude to Srimati S. Anjani Madam, IQS coordinator of college. She has encouraged and guided us as how to make a grand success. My heart goes out to thank our respected participants for accepting our invitation, coming to this national webinar, and encouraging the moral of the speakers by your active presence. I thank you from the bottom of my heart. Also, I want to express my heartfelt gratitude to all the persons presented today. I am very happy to say that participants belongs to Telangana, Andhra Pradesh, Tamil Nadu, and also Karnataka. I would like to say my sincere thanks to V. Samshirao sir, HOD and convener of this webinar, Since 10 days, he is working very hardly and prepared all the material for this webinar, and it happened as grand success due to your hard works only, sir. I would like to say my sincere thanks to all the members of the faculty members of the Department of Mathematics, Kakatiya University also. I would like to say my sincere thanks to the heads of various departments and the faculty of our college. And special thanks to S. Ramesh, Assistant Professor of Commerce of our college. I would like to say my sincere thanks to my colleagues of the Department of Mathematics, who are very motivated and dedicated colleagues who know their job and result oriented. Finally, I would like to say my sincere thanks to all the persons who have dedicated their work to make this webinar as a grand success. With these warm words and kind wishes, we move to the end of today's webinar. Thanks to one and all.
Okay, with this, we conclude this session. Let's call it a day. Adios. Bye.
Bye, ma'am.